I should probably say hello out loud to make sure my mic's working.
It's working.
Okay. Great.
Nice to see you again, Jake. It's been
nice to see you too.
Long time no see.
Yeah, really. This is fun.
Sorry, Cesare has just informed me that we are now in streaming, so we can start officially. So good afternoon, everybody. I'm Matteo Bianchi, assistant professor at the University of Pisa, and it is really a pleasure for me to welcome you to the 10th edition of the Robotics Research Jam Session, which is organized by Centro E.Piaggio, University of Pisa, with the Soft Robotics for Human Cooperation and Rehabilitation Lab of Istituto Italiano di Tecnologia. And I'm now leaving the stage to Professor Antonio Bicchi, who started the Robotics Research Jam Session in 2011. Thank you.
Thank you, Matteo. Thank you, Paolo and Cesare, for organizing this year in this new modality. Can you see my screen?
Yes.
Okay. So, yes, this is something that we organize since some time, and the idea is that, as you know, it's really a brainstorming workshop. We started this in 2011, and so the idea is that it's very casual. This is where jam session comes from. There is a loose thematic thread in these meetings that we have every year. This is the 10th edition because in a couple of years ago we had two sessions in the same year. The attendance is open, so during the live meetings that we had up to 100 people attending in person to the talks. And the reason is the high quality, the very high quality of the speakers that we managed to have in this little series. You see the names in this slide. So most of them are famous colleagues that really contributed to the community, and it was an honor, a pleasure to have them here. Just like this year, where we are going to have more distinguished colleagues. And the fact that we basically go, just speaking about what is more exciting in what you do, without having to write papers or submit things, it makes things nice. So the program this year, I will not read it into detail because we have little time. But we have Arasha Giudani, who is a brilliant researcher at Istituto Italiano di Tecnologia, just got an ERC, who will speak about ergonomics and robotics. Hermano Igo Krebs from MIT, giving us an overview of the 77 lab. Paul Verschure from Catalonia. Jake Abbott from University of Utah, Matteo Cioccarli from Columbia University in New York, and then we will have Mark Spong and Alireza Mohammadi giving a talk from Texas, Carlo Trompetto, a professor in neuroscience, tomorrow giving a talk from the University of Genova, giving a talk on rehabilitation, and Andrea Davella on muscle synergies, Lorenzo Masia, upper limb soft wearable exosuits, and then we will move to more robotics teams. Lorenzo Sabatini from University of Modena and Reggio Emilia, Dimos Di Marogones from KTH, and finally Paolo Salaris, who is a new professor that we hired last year in Pisa, and will give a presentation on online perception-aware trajectory generation. Paolo is also one of the main organizers of this jam session this year, so thank you very much for doing this. The real reason for running jam sessions is that we have the blessing of excellent students. They do a lot of work for us. They do basically all the work we do, and at the end of their studies, we feel that we have a debt. And our best way to pay our debt to those students is to make a panel that reads their thesis and listen to their thesis, to their defense, that is the best that we can get to, the best in the world, actually. So this year, in a separate session, there are presentations of our students, Franco Angelini, that was reviewed by Alessandro De Luca and Mark Spong, Giuseppe Averta, who was overseen by Andrea Davella and Mattei Ciocarli, Andrea Ciullo, who had the pleasure of having Herman Nico Krebs, Paul Verschoor, Carlo Trompetto, Simone Fani, Jay Cabot and Lorenzo Masia, Anna Mannucci, Dimos Di Madrogonas and Lorenzo Sabatini. So that's the reason why we are here, because we are asking you to be part of these panels that are our best gift to our students. Let me quickly go through the topics that are to be discussed in the defenses this year. Franco Angelini will present on the problem of planning and controlling articulated soft robots. And it's basically, the topic is how to control articulated soft robots, robots that have soft, flexible parts that you want to have not only feedback, but you also want to have feed forward to preserve the softness of these devices. You need to learn how to compensate gravity in a soft mechanism. You see here on the right picture of how a robot that has learned motion without compensation of gravity makes mistakes in doing that, and the method that Franco presented to compensate for that. It cannot be all feedback, because feedback tends to stiffen the mechanics of the robot. But thanks to this learning behavior, Franco makes a nice result here. Franco's work is very much analytic. He also tries to generalize on a sound theoretical basis, to generalize to compensate gravity, but also to vary velocity. And for instance, he shows that if you have only 5 examples of different learned motions at different velocities, then you can generalize to any velocity profile. Also, Franco also asks himself how to regulate the robot impedance, when you should be stiff and when you would be soft to achieve a result. And again, on an analytical model, he shows that for some tasks you want to be stiff, and for some tasks you want to be soft, for instance, for preserving stability. And then he applied these ideas of articulated soft robots to tasks where you have locomotion tasks and manipulation. So for instance, here he has implementations done in the UK, where he was visiting in Edinburgh, where he shows how to adapt the impedance of a robot to match different environments. Next is Giuseppe Averta, who will defend on human-aware robotics, modeling human motor skills for the design, planning, and control of a new generation of robotic devices. He was supervised by Matteo Bianchi, and myself, and reviewed by Andrea Davella and Mattei Ciocarli. So what did Giuseppe do? He has 3 parts, basically. One is taming the complexity of human motion generation. He gathered extensive cross-modal human data. Then he did functional PCAs showing dynamic evolution of this data, not just the classical PCAs that are static in time, but showing the dynamics in time. And then he applied this to normal, constrained, and impaired conditions. As a result of this study, he was able to apply to the design of nature-inspired prosthesis and the assessment of motion impairment. He studied the wrist geometry, for instance, and it's the role of the wrist in humans, and then he did the design of an adaptive synergy wrist for prosthetics, contributed to actually. An interesting result is the quantitative analysis of pathological synergies, those synergies that you observe in patients that have correlations of muscles, motions that are not normal. And he also designed a new device that you see here for dynamic stretch reflex threshold assessment. Third part was the transfer of human principles to cobots and autonomous robots. As you can see, by giving these very short summaries of the thesis, I also illustrate a little bit the spirit of the group at large, and it's something definitely in between robotics and humans. This is natural motion, embedding human likeness in robot movements, making robot move human-like, planning impedance behaviors in physical interaction, and eventually and finally giving a human-inspired distributed architecture for grasping, from data-driven to embodied intelligence, all the way down in a nice architecture that he proposes. A third candidate is Andrea Ciullo, who already defended this morning. He spoke about soft robotic technologies for a novel generation of supernumerary limbs. He was supervised by Arasha Giudani and Manuel Catalano and myself. And he basically developed active supernumerary hands for grasping, compensation, and augmentation. The idea is to use the soft hand, which is something that we developed in the recent years, as an extra thesis, as a third hand. This was for both augmentation tasks, where, for instance, he tried to find ways of augmenting the power, reducing the vibration, or for compensation in post-stroke assistance and rehabilitation. He did work in both domains, mechanical optimization, experimental validation with subjects, and in compensation, he opened up some new directions that were really not there at the beginning of his thesis, where he tried to use this extra supernumerary hand for both chronic stroke patients and subacute stroke patients, with some results that are preliminary but very, very interesting. A fourth candidate this year will be Simone Fani, who will defend on wearable haptics for advanced human-robot interaction, and Simone was supervised by Matteo Bianchi and myself. He has three main topics. His real topic is haptics, both the analysis, the study, and the device, the development of the device and the validation. So he did a very thorough jobs on different modalities of touch feedback, and he had worked on devices, high-frequency rendering of vibrations on the fingers of a prosthesis and bringing them back to a patient. This was all clinically proven. Then he applied other devices for detecting, for replicating the force, both normal and tangential, in an environment for telerobotics application, and also other devices for rehabilitation and augmented reality, as you can see here. So these devices that he developed are different, and he did all the engineering and the testing. The applications were to prosthetics, to telerobotics, to rehab. The final candidate who defended already this morning is Anna Mannucci, supervised by Lucia Pallottino, and she was doing intralogistics with integrated automatic deployment from one to multi-mobile robot systems. The committee was formed by Matteo Bianchi, Lorenzo Sabatini, and Alessandro De Luca, Dimos Di Maragonas, and Darasha Giudani. And you can see here, if I start the videos, yes. So the topic is coordination to reach a target point, avoiding collisions under non-ideal communication, delays, packet losses, etc. So things go normally very well, but when you have delays and packet losses, things get complicated, as you can see, as you could see there. One of the main problems is to avoid deadlocks and live locks, and you have videos here that show how the methods of Anna help to manage traffic in an environment that is a logistic environment, industrial logistic environment, and to coordinate multitask in a null space-based inverse kinematic approach that is using for mobile robots the general ideas of reverse priority control that were proposed for articulated robots by Flacco and De Luca a few years ago. Okay, with this, these are the presentations of the PhDs whose reviewers are part of this panel. If I have 5 more minutes, Matteo, I could give a brief, I steal 4 minutes, about the activities. Normally, at this phase, every year we give a little snapshot of what research we do in our group. But I think I already illustrated some through the presentation of the PhD thesis. So let me talk about something that we did recently in a more general setting with this Italian Institute of Robotics and Intelligent Machines that you see here. So this is the IRIM, the Italian Institute of Robotics and Intelligent Machines. It's something that we started very recently, whose idea was to, the motto is AI fleshed out. So whatever AI needs to interact with the environment physically is of interest to IRIM. And it was founded roughly 1 year ago to communicate the potential of robotics research and industry to society and leaders throughout Italy. So the promoters are names that you probably know already because they're, the whole community is reflected in this institute. We are all together, so we had 250 roughly members in 2019. We had the first conference in October, very well attended, 500 registrants, 100,000 visitors in the robotics exhibit that we did at Maker Faire in Rome. So things were going strong with this idea of having an institute for robotics. And then Italy was hit early and hard by COVID, as you all know. And I think it's sort of interesting to discuss with you, especially those of you who are not from Italy, what was the approach that we followed, and if there is any use of it, we would be glad to share. So what we did as a national community was to have daily meetings from the end of February 2020 until mid-April, following for a few weeks then, with a 3-pronged strategy. First is we decided that we should listen to the needs that came from the field, and then give short-term response and longer-term response with some pilot projects. So let me, what does listen to the needs mean? We started doing extensive interviews with health system operators, nurses, doctors, and also all those that were exposed to contagion. So we had a questionnaire that you see here. We received more than 200 answers. We did a text analysis. We understood what was important and also something that was not important, something that we thought would be important, but it was not actually to the people that were really doing the work there. Then we also did a collection of pilot projects. All those projects that have high TRL, technology readiness level, that were proven in clinical or lab environment already, but not yet available commercially. You know, there are many projects that could be available, but not really in the moment where they were needed. So we classified them based on which application, from where, what's the TRL level, the documentation all documentation that each group could provide. We listed some 70 pilots, and then those are available in our website. But probably one of the things that was hottest was giving a response in short term. The question was lingering around. There was even a press on the press, an article asking, anyway, those robots you talk about, where are they now that we need them? And it was not just because of this, but it was because we felt compelled to provide an answer in emergency that we wanted to be not in 5 years from now, not in 10 years from now. We wanted to give an answer now and wherever needed, not just in labs or in few hospitals, but all in all the hospitals in the countryside of Italy, where the COVID was raging, and in short time. So that was very difficult, and we decided that to do this, we needed to be, somehow humble, I would say, do something that is not maybe the most sophisticated idea that we have, and that might be proven and working in 5 years from now or 10 years from now, but something that could work now. Maybe look back at what the robotics technology has provided in the past 10 or 20 years and make it available to real people. And to do so, we came up with a scheme of a coalition with the world of makers. The idea basically is that there is a matching. We created this site, Tech for Care, which is an open platform for sharing emergency resources and projects against COVID-19. It's basically 3 parts. The collection of needs from the community where people would say, this would be, I would need this technology. I would need to solve this problem actually. And then a solution that might come from research groups propose or, anyhow, who has an idea of how to solve and provides open source this solution. And the third group of those who can build and realize, remember, as you probably, some of you still have, at that time, it was impossible to go out of the house. Everything had to be done at home, basically. You could not bring a robot to an hospital. But so the idea was to make things available locally to a small makers group to provide the given solution to match the need. And here are a number of projects that were shared with the whole community. You can basically go there. You have some that are certified, some that were non-certified, providing all the details of how things could be used safely or not. Our group especially focused on one of the needs that were most prominent through our listening campaign, the telepresence, that was in big demand for isolated and immobilized patients. Telepresence robots exist already, but they're not available in large quantities. Vacuum cleaners instead are available in large stock. You can have them from Amazon. You could have them from Amazon even during the lockdown. And the idea was very simple, very humble. Modify the existing hardware with new open software that was made possible by Roomba, by iRobot, and then make the project open and available to makers to build. So LHF Connect, LHF stands for low-hanging fruits, something easy to reach in the emergency. It's fully documented open project to build a telepresence robot with available hardware and open software at around 1,000 euros. So the full documentation is available online. You can find whatever it needs to build one, to sanitize, download the software, have a repository, the 3D models, all the facts are there. And it was supported by IIT and University of Pisa mainly. And here is the implementation. I hope you can hear the sound. Can you hear the sound?
Yeah, not so clear in a clear way.
Okay. Here is a real scene in a hospital. A patient that was there for a couple of weeks. You can see their relatives.
And Antonio, we cannot hear your voice now.
Okay, so the robot was also used for doing medical consult. The robot is active in a COVID area. Now the COVID area, luckily, I mean, fortunately, is closed in the hospital, but it was also replicated in several other hospitals and care homes, elderly care homes. For instance, here is one in Lombardy. They really took down from the internet all the plans, build one or two for their use, and went ahead with this. So with this, I think I would like to close. This is the group that worked in this project, and we really hope that the use of these robots will be less and less in the future. But we think that it was important to show to the world that robotics can be of use, not tomorrow, but even today. So thank you very much, and let's go. Thank you again for being here, for being with us for this jam session. Unfortunately, we are not there in person, but I think the excitement is completely there. Thank you.
Thank you very much, Antonio, for the nice introduction to the sessions and the research and also the activities that have been done during these critical times. So now we are ready to start with the talks, and the first speaker is Arash Ajudani. Arash is a tenured senior scientist at the Italian Institute of Technology. He leads the Human-Robot Interfaces and Physical Interaction Laboratory. He's a recipient of the European Research Council Starting Grant 2019 and the coordinator of the Horizon 2020 project SOPHIA, with a consortium of 12 partners from the leading European research and industrial organizations. And in his talk, he will present the early achievement of the SOPHIA project, which aims to create a new generation of core robotic technologies for socially cooperative human-robot systems. So thank you very much, Arash, for being here.
Thank you very much, Matteo. Can you hear and see my slides?
Yeah.
Perfect. So I would like to also thank you and Antonio and all the team in Centro E.Piaggio for having me in this list of really high-impact talks. I really look forward to these 2 days events. I was on the other side a few years back, one of the PhD students, and dreams come true. And and at the moment, I'm giving a presentation on one of the projects that actually I'm coordinating, but also together with the University of Pisa. As Matteo kindly anticipated, the project is called SOPHIA, and the SOPHIA stands for Socio-Physical Interaction Skills for Cooperative Human-Robot Systems in Agile Production. I would like to spend a few minutes just to tell you more about SOPHIA general concept, and then I will just go specifically on new works that my team specifically have been doing and contributing to this project, as this project is a really multidisciplinary project with so many partners. So the challenge we are trying to tackle in this project, of course, if we can summarize it in 3 main aspects. One of the biggest is that the current production systems are, let's say, not flexible enough in terms of adapting to the workers' needs and helping them in repetitive or basically effortful conditions. That this has led to the evolvement of so many problems, including work-related musculoskeletal disorders, and the numbers are really bad in most of industrial countries, especially Europe. Is estimated to spend 240 billion euros a year in costs associated with lost productivity, absenteeism, etc. The flexibility also actually translates to the production flexibility. That's why SMEs or the companies, industrial companies, or as well, let's say, warehouses cannot really provide this flexibility. That's why we see a lot of outsourcing going on in US or in European countries, and this is another big issue. And also the well-known problem of labor gap, which is estimated to be by 8.3 million people, which means that in 2030, 8.3 million people will be leaving work, and this gap will be not filled by the young workforce. So what's the problem? We have been taught that collaborative robots can be a good, let's say, flexible solution to cover all these nice aspects that we are dealing with. But the problem is actually that the way we are using collaborative robots is kind of close to what we have been doing with traditional robots. In fact, we are not exploiting the full potential. We are taking them outside of these really protected areas, but we are putting them in less protected areas, although we're asking them to do the same pick and place tasks, very defined, very, let's say, specific tasks that they're supposed to do. And when we take them out to work with the humans, we are too stressed about connecting humans and robots, and all the collaborative concepts mostly are around the concept of avoidance, safety, and this is also good to remember Fabrizio Flacco's brilliant work a few years back, and also to memorize him, that he started this with some other colleagues. He started this really nice safety-based research. And the point is, maybe we can actually build on top of that, not only ensure safety, but also try to bring humans and robots together. In fact, the motto of SOPHIA is not to, if we have basically 3 players in an industrial setting, humans, products, environment, and robots, what we want to do is to basically ensure that humans have a better understanding and adaptation to robots and vice versa, and robots can adapt much better to the products and environmental changes. This is actually what we want to do. And of course, there are so many components and technology enablers and, let's say, different aspects that are contributing to achieving this. For instance, we are trying to improve the robot autonomy. We are trying to blend social and physical aspects of collaborating humans and robots, because usually they're treated separately, which is not really the way humans actually work together. And we want to provide a framework of socio-physical human-robot interaction. And of course, to be able to implement our ideas, we need new robotic assistants, such as collaborative robots, which are agile and with a good acceptable workload and payload, and also wearable systems that are somehow better, somewhat, or maybe to a major extent better than the conventional systems that basically mostly are avoiding movements and a lot of constraints that they provide. SOPHIA consortium is very rich. So IIT myself is the coordinator, and we have University of Pisa, of course, University of Twente, and so many brilliant universities that are actually contributing. We have a decision-making policy, let's say, column. ENAIL, DIN, and BAWA are contributing to the new standards, safety measures, and things like that. And we have, of course, a good list of industries such as Volkswagen, Handcam Gears, and Hydria. And we have a really good list of digital innovation hubs to be able to exploit results. Coming back to research, I would like to tell a bit more about the contributions of my team to this project, which is, in this presentation, I would like to mainly discuss 3 items, which is mostly improving production flexibility, improving human comfort and ergonomics, and of course, advancing robot interaction autonomy. So when we talk about improving robot flexibility, I think what we talk about, like, basically advancing the automation of the robots, but most of the cases that we would like to advance the automation and make that the humans and robots comfortably and intuitively work together are not mostly along the process of, let's say, not along individual processes, but between the transitions. Because most of the processes can be really automatized with minimum costs. I'm not talking about SMEs, but in small ones, but in medium and large companies, you can actually automatize all these aspects. But the problem is between the transitions. When one process finishes to the other process, how we can deal with that. And one of the most famous problems is, of course, the box filling task, when the products are coming in, outside of a machinery device, or let's say a fine-tuning device that are providing the products. The problem will be how now we can make flexible systems that can detect objects, pack them in a really nice and human way, and also be collaborative so that they let humans actually to intervene. So if you see in this plot, we have created, based on one of the use cases we have in SOPHIA, we have created a small demonstration scenario where Franca Amica arm is receiving some of the components and is trying to basically maximize the placement of these gears, let's say outer shell motors inside a box in an autonomous way. And of course, this would be flexible enough to be able to, let's say, deal with the uncertain conditions and also the human intervention. So what we have done is basically through the vision system, we are trying to see the occupancy map, occupancy grid at each iteration and trying to understand what is the best way of fitting the basically these objects. So the best way would be, let's find where is the best option, which is basically a place that is maximizing the placement of the objects in a surface, and we start sliding towards that. The reason for that is basically if you have some certain uncertainty in the vision, then you can exploit the compliance of the robot and actually avoid the collisions which you could not basically precisely measure through the vision system, or you had some planning, let's say, uncertainties. Therefore, we also came up with some sort of self-tuning impedance control problem that by going through the dynamics of the robot, we can actually decompose the stiffness and damping of the robot, knowing that they are symmetric and positive definite. We can decompose it through the singular value decomposition, knowing that what are the stiffness values and damping values in the major directions, and what are those directions that actually comes from the planning and the occupancy grid. So through this and some techniques, we are able to actually adjust the impedance in a way that it exploits basically the environmental constraints in the placements of the object very close to each other, so maximizing the number of points that we can have, number of items that we can have in the space. So this is one of the demonstrations, like as you can see in the video, through the vision system and this Aruka marker, we understand when the system is arrived, occupancy grid is updated, the planning is done really online, and everything is happening in autonomous way without any pre-programming. The vision also tracks the box. Here you can see the human is putting randomly two objects because we want to finish it as soon as possible. Occupancy grid is updated in real time, and then again you can see that the system is maximizing the numbers and detects the empty boxes. If the person changes the box, you can see that in real time we are able also to see if the box rotation or placement of the box in the robot workspace has changed, and robot updates all the transformations that we have and helps with the human to perform this task. The last piece is basically, you can see we don't have much to play with. I will go through some more details of the results, and it becomes sort of a peg in the hole problem that we also dare tune the impedance parameters to be able to perform the task. So you can see, starting from a very rigid, very empty box, there's a lot of options, but we want to maximize the number, so start from a corner, and it goes all the way. We see that when the constraints are happening, especially it lets people, humans, to help the robot to speed up the process, but the robot adapts to the task which is being happening. Again, here you can see that the algorithm is able to find where the objects can be placed and finds where is the starting point, so I can collide, avoid collisions, and basically eventually to maximize the number of objects in the scope. The last bit becomes a peg in the hole problem, so the impedance parameters are adjusted in a way to perform the placement without any sliding. Just to give you an idea why self-tuning is important, for instance, if we have a cluttered, let's say, scenario such as this, if we want to put the object here and the vision is giving us some bad information, so the problem will be if we are rigid in that sense, we will get stuck there, have really high interaction forces, which is bad for the object or for the robot, and the task will definitely fail. But if we have self-tuning algorithms, it can make the robot comply with the environment without actually knowing a precise, with having some uncertainty in the dynamics of the robot, dynamics of the task, but also vision, we can perform the task. So now that we actually made these boxes, filled these boxes, one of the problems would be, let's now palletize them, because in SMEs or even in the large companies, these are the tasks that are usually done manually. So what we want to do is also to help people to be able to do these kind of tasks basically very efficiently and very autonomously, most of all ergonomically. So what happens here is that what we want to do again is to maximize the number of objects in boxes in the palette. So we have written and actually exploited and customized an optimization problem, which tells you number of boxes. By knowing the box shapes and geometry of the boxes, it tells you how you can maximize the placement of the boxes in a palette. For instance, running a simple experiment, asking humans to follow our optimization and humans just to follow their intentions, we can see that we can really reduce the time of the let's say boxing and arrive to a maximum number of let's say palletizing boxes only by the humans, but only by using our optimization technique, which is real time. So now we can actually integrate this optimization technique, sorry, into our robotic, let's say, control system, and sort of actually proposing some role allocation techniques, which robot decides in which, let's say, which configuration will be the best to perform the task. So if the box is reachable and graspable by a mobile robot, it can be done by the robot itself. If it's light enough that human can contribute to speed up the process, it can be assigned to the human, and the human has the permission, let's say, not the permission, but has the possibility to move this with the minimum risk of musculoskeletal disorders. And if the box is too large, then it can be a collaborative. Everything, and I'm telling about, they are all, let's say, implemented autonomously in our role allocation framework. Just to quickly go to the experimental setup. So we used our MoCA, which is a mobile collaborative robot assistant robot, which is composed of an omnidirectional base and a collaborative robotic arm with the PIAggio soft hand, which makes our life way more easier in grasping and manipulation. So what we had to do is, of course, the first thing was to make a whole body impedance controller to know where we are and what is the level of interaction that we have with the environment with respect to the world, right? Because we want to know where we are and what forces we are applying to the robot. Not only that, but we also had to control the mobility of the system. In the left side, we can assign larger mobility to the base. In the right side, same planning, but with a larger mobility at the arm. This is really important in such tasks because you want to reach without any collision with minimum, let's say, problems. Of course, there's some theory behind, and I'm not going through the details. Again, we adopted our vision system using Aruko markers to understand what are those boxes. Only Aruko markers provide you the weight and the size of the boxes. This is very simple mechanism. For instance, in Amazon warehouses, all these are done autonomously. You don't have to really worry about this. The stamps can be there, and the vision system can detect everything. So based on this is one example of the robot, which actually autonomously just navigates and scans the boxes and loads in the optimization of the box maximization, which is sort of role allocation, right? So, and also the palette detection is done autonomously through the vision system. When we have this can happen. So screening, knowing the boxes, screening, and basically scanning the palette. And now the situation starts. On the top right in the monitor, you see that the boxes are color-coded, which gives the human not only the placement, that the plant placement, the optimum plant placement in real time, but also the boxes that are in low weight that the human can contribute to the grasping of it. So here we use some magnetic grasping because at that particular moment suction cups, suction grippers were not available, and PIAggio soft hand wasn't as we know, wasn't a good option for grasping large boxes. Therefore, we customized and we built this magnetic just to show the let's say the experiment. So here you could see that the human could use the small box and place it in the dedicated space. But here, since the robot is not dual arm, it needs some sort of, let's say, how can I say, the collaborative, let's say, box filling that it calls the human. So basically the human is actually helping the robot so that together they can actually perform this box fitting task. And following, basically, this is the purple one which is appearing in the surface. So together they are putting it down. So we did some experimental analysis on 10 subjects, and people were saying that, of course, given the weight of the objects and the size of the objects, collaborative task was easier to perform. The manual performance required greater physical and psychological effort, of course, because if you don't know where the placement of the boxes is, you have to try it several times to find the best way of doing that. And the collaborative system led to a broader satisfaction, we believe, not only because of the performance, but also because of the attraction of the system. Imagine workers working in more attractive warehouses that robots are around can be more satisfying than manual warehouses or production systems. And in the end, the HRC presented really promising results in this framework. How much time do I have? I think I have still like 10 minutes. Yeah. So now that the box is filled, the next question will be, can we actually introduce the same robot in a production environment and start to move this box with a pallet jack around? So we looked into the system instead of using humans to move the pallet jack. As you know, pallet jack is a really constrained system. You have a bicycle, 2 degrees of freedom, 1 translational, 1 rotational. If you want to move from point A to B with certain, like from here to here, if we want to do this, I myself have to do 10 rounds of going back and forth to be able to put it from here to here. But with some optimization, a robot can do in one shot, calculating the optimum path and bring it there. So this was the main idea, to use same collaborative robots that are doing other things to replace and reposition the pallet jack, which is filled by the human and stuff like that. I'm going a little bit faster. So here you can see the simulation results that basically, even with the obstacles, here, sorry, there are no obstacles. We have a really good path planning, although that the robot and the pallet jack are coming into a dynamic serial change. The robot knows its own, let's say, kinematics and dynamics, because it's omnidirectional. It has 10 degrees of freedom at task space, and the pallet jack, it has only 2 degrees of freedom. So planning is kind of complex, right? So we have to take it into account. And then we also worked on obstacle avoidance using laser scanners. So mapping static obstacles for the moment. When the robot is moving, it can actually detect static obstacles on the path going towards reaching a pallet jack, also on the way back. So let me give you a quick video of, show you a quick video of this experiment. This is our MoCA. MoCA roughly knows where the pallet jack is, and it goes there, but it uses this the vision system that we developed before through the template matching. You can see on the top left to detect the handle, and then through the fusion of the vision system and the forces that you can see in this part, it detects the handle, grasps it, plans online in real time, and basically the objective was to place this with same rotation next to this pallet, right? So the robot actually is able to plan and bring the robot and arrive there with a in a single shot, and basically leave the pallet jack right next to it. So as you know, it's not really easy, not only in terms of planning, but also it's not super safe. You might hit your ankle, and this can be quite disturbing. These are the results of the experiment that I showed you, the planned, the actual, and everything else which was shown in this video. Another work that we have been doing is also trying to make this interaction more flexible in a production system. We have recently proposed a new collaboration system which will be presented in IROS. We received the acceptance notification today, and I'm happy to present it also today for you. We call it the visual haptic guidance interface, where the robot actually through contact, you can navigate and take the robot anywhere you want. Basically, it can just follow you. And when an interaction is happening, like asking the robot to load some objects, then you can actually ask the robot to switch to visual guidance, and the robot actually follows you by detecting online all the obstacles and removing all the obstacles online, and will follow you to reach to a certain path. Imagine this is like a more flexible and automatic loading mechanism, but it offloads you from all external loadings and makes you work in a more healthy conditions. Let me quickly go to the video. Of course, there is a lot of components, a lot of interaction between human tracking. We use open pose, we use 2D skeletal tracking, and then we extract 3D skeleton using 3D skeleton reconstruction. We have a whole body task, and then we have the external forces detected through the admittance control and haptic interface. Of course, we put in our whole body impedance controller, which is sort of a causality between admittance MoCA and impedance controlled robot in a whole body let's say, scheme. So this is the scenario. First, through the open pulse system, robot comes towards the person. It switches as soon as it detects the contact. It switches to the follow me mode. The person can simply go, reach, bring it up and down, and just by clicking, the robot grasps and actually starts loading. So this part is autonomous only, and it puts, let's say, in its carrier or whatever. This is about 10-15 kilograms. We don't want the person to carry it and let's say to remove the loading from the person. So what happens here is, again, it comes back to the human and in a haptic guidance mode, but any time that the person leaves it and moves from the obstacles, you can see that it switches to the visual follow me in real time, removing the obstacles, going to the first via point, and then following the person, as you can see in this video. So you can go long distances, and the robot will still be able to follow you. This is the results of the experiments. More will be available in the paper soon. That basically these are the points that the robot is planning to the path that the robot is actually following. This is the human path, and these are the obstacles in the environment. Matteo, how much time do I have? Because I lost Wendy 5 minutes.
You have still 5 minutes.
Okay, thank you very much. So one last point I wanted to tell you is advancing robot interaction autonomy. Of course, in industry, we have a lot of peg in the hole, which is assembly tasks. And the conventional technique to do this was through remote center of compliance, where we have passive elasticity that gives you a certain stiffness in the direction of, let's say, insertion, but more compliance in the rest of the directions, so that it can actually introduce you some compliance and some passive compliance to be able to avoid interaction forces that are not good, but go against interaction forces that you want to have, like friction, for instance, in the peg in the hole task. So we thought of implementing this in active impedance controlled robots. Of course, this is a sort of classical technique, but we built some sort of intelligence on top. One thing was we brought the vision system to understand what direction is the good direction that we want to be stiff, and the rest of the directions we had this control action by measuring the external forces through Alessandro De Luca's famous work. We actually adapted we call it adjusted equilibrium point. So the robot was compliant with in response to the external disturbances, but by compliance, I don't mean that we changed the impedance, but we changed the equilibrium point so that the robot actually moves back. It's the same behavior because basically the dynamics you feel is basically as if the robot was compliant. And the vision system was telling you in your singular value decomposition which is the stiffest direction and which directions you need to be compliant. Long story short, this is the one video of the experiment. You can see that basically even we have some degrees of mismatch. If you're stiff, if you do this peg in the hole, of course you will break the tool. But through this control framework, you can actually really nicely adapt and perform this peg in the hole task with minimum interaction forces. And this ASUS camera with our template matching system again was used to know, okay, here I have the point cloud data, I can apply the PCA, and I understand that in what direction is the insertion direction, and in what direction I need to be stiff, in what direction I need to be compliant. We added intentionally some mismatch. So here you can see that this mismatch was added, and then after performing this control action, we were able to do this really challenging task, which is one of the important tasks in the industry. Some results, of course. Let me just go to the very last work. One of the main pillars of the SOPHIA project, of course, which deserves a lot of attention, is we plan to improve the ergonomics of the people. Although my team is not directly contributing, and this is in charge of University of Twente, but as Antonio kindly mentioned, I recently won an ERC project, which actually I'm applying robotics techniques in understanding how we can model humans and human factors through really good, let's say, real-time and highly, let's say, performing robotics techniques. So this was the initial work we did last year, where the robot could adapt to different people and improve their ergonomics. For instance, if there's a handover task, through some dynamics and modeling, we could know that what is the best way of performing the handover task, which minimizes the effect of external loading on the joints. And when you want to do some co-manipulation, let's say with a subject, that what is the best configuration that minimizes the effect of external load, but also maximizes your manipulability in terms of force and velocity control. So we extended this to an algorithm within the RC project, which is very relevant to SOPHIA. We hope that we can connect these two systems together to actually provide a system that can start from scratch, not knowing you, and model you in, let's say, more than it's about 20 to 25 seconds, and then it will start everything from scratch. So it basically, you can see it suggests some postures to you for the identification of the parameters, and you follow these postures immediately, then it will recognize you and always have your parameters in mind. So you can see this is a very nice demonstration. Everything is green, which means that the effect of external load on the joints, where we call it overloading, is minimum. The moment you start using this, you can see that the lights are coming, telling you which postures are good, which postures are bad. So trying to help you with assuming some good postures. This is also one of the IRIS papers that got accepted today, and we are happy to extend this in more, let's say, sophisticated scenarios. Thank you very much for your attention, and I would like to conclude with this logo of the SOPHIA project. SOPHIA is quite young, so we are at 7 months. We still have 3.5 years ahead of us. Hopefully no more COVID will block us from advancing within these topics of research. Thank you very much.
Thank you very much, Arash, for a nice presentation. So just to briefly mention that the event is also live on YouTube, so we invite the attendees to write their questions to the speaker using the chat. But I would like to start with one question to Arash. You have presented many interesting things and also a very exciting framework for new modalities in robotics. So the question is more philosophical, if you prefer. So in view of these new collaboration modalities, where there is also an important part of autonomy of robots, do you think we should redefine, considering also human modeling in this interaction, the paradigm of shared autonomy in robotics? Do you think the times are now mature for this new reconsideration, also in light of the neuroscientific inspiration of your work?
Thanks a lot, Matteo, for this really nice and actually stimulating question. I think, as you mentioned, I think if you think about like Paul Fitt's first role allocation or shared autonomy idea in 1951, he was saying, let's consider who is the best for what. Robots are the best for repetition, precision, humans are the best for supervision and things like that. But through time, I think this is changing a bit. Robots can not only take into account repetitions and things like that, but they can also know more about your states, psychological state, physical states, loading, vibration, the work of Andrea, for instance, this morning where he was presenting. And also robots can know vice versa. Also humans can know more how they can actually transfer knowledge to the humans. I think we are going to a paradigm that this shared autonomy and shared control frameworks need to consider way more than yes, no, or very, let's say, discrete states. I think these states can be varying in time, for instance, and also include human, let's say, human taste. If somebody prefers to do it in one way, I think the robot should be able to let's say, adapt to the way the human wants. This is a really nice question. Of course, there's a lot of work on this as well. Through people are trying to work through the graphs and the planning and role allocations through the graph theory. But still, as you know, maybe there's a lot of work still to be done to be able to include human intention and robot capacities in one single framework.
Thank you very much, Arash, for this exciting answer to this challenging question.
Thank you very much.
Okay, Manolo?
All right, can you hear me?
Yes.
Okay, so Arash, thank you very much for your talk. Exciting, very, very nice and impressive.
Thank you.
And one interesting thing to me is that you are going towards this, adding this social sphere in the classical template of physical human-robot interaction. Can you comment a bit more on this, on basically how much this will add to the interaction between human and robot?
Yes. Thanks, Manolo, for this question. I think, the main reason we are looking into this is so far robotics has been looking at two types of interactions completely separately and individually. We have physical interaction when humans and robots are doing tasks together, and we have non-physical interaction where robots are used for education purposes and stuff like that. But looking at industry, there are cases that humans and robots coexist. Not all the time they collaborate, but some phases of this task they might be collaborating and physically being coupled, right? So we cannot really distinguish and have two different frameworks that you talk to the robot and you use this social framework, and then you have the physical part that you're switching to another type of framework that you're basically trying to do a physical, let's say, physical task with the robot. In the end, what we are trying to say is there's a lot of information already in the social aspects. For instance, human gesture, human body, human, not only through the audio and these language, there's a lot of information that this can be used for physical interaction control as well. For instance, one of the things that we are trying to look into is to distinguish if there's a human in the environment, if this human has a collaboration intent or is just an obstacle. For instance, if you're approaching to a robot and the robot is doing its job, so how the robot should know that you're planning to work with that robot, or it's a potential risk for collision. This is the thing that implies that your physical performance should change from a social aspect. So we are trying to understand, this is one example, that there are many examples like this, that these two are really interconnected. So you need to know the social aspects to be able to give the right physical response and vice versa. Of course, in rehabilitation probably, or in social aspects, people a lot use social cues like voice and things like that. But since our focus is industry, voice is definitely out of let's say, choice, because we don't want to add more noise to the existing noise in industrial environments. Therefore, we are relying a lot on the vision and gestures and things like that, but not gestures that you have to remember what this means for a robot 15 million times. Gestures that are natural. Of course, we are in the beginning of the way, as you know, and hopefully we can find a way out. Thanks.
Thank you, Arash. Are there any additional questions to Arash, or otherwise we can move to the next talk? Okay, so thank you very much, Arash, for your presentation. The next talk will be a talk by Dr. Hermano Igor Krebs. Dr. Krebs is a principal research scientist and a lecturer at the Mechanical Engineering Department of MIT. He also holds an affiliate position as an adjunct professor at several prestigious universities worldwide, and is the recipient of several honors and awards, and has been among the founders of companies that work on rehabilitation medicine. And in his talk, will provide an overview of the 7070 lab at MIT. So thank you very much, Dr. Krebs, to be part of these sessions, and the stage is yours.
So thank you very much. I hope you guys can be seeing my slides. I believe you are. But if things don't show well, please interrupt me. What I want to talk a little is about the 77 lab and the different activities that we have there. Most of the work is done by the team. And I have to say that I am very proud of the team that we have there. Many of them had already left and took faculty positions in different places or in industry. But it's a very, very cogent and very, very brilliant team that we were able to assemble there. And we focus in three main areas: rehabilitation robotics, and maybe this is the area that I have a little more history working on it. But I decided today to talk a little about other things besides rehabilitation robotics and introduce you to two other areas that we had been working quite a bit, which is agricultural robotics and digital transformation. And I'll try to do the overview going through two different projects that we are pursuing, funded by industry. The first one is on trying to use a robotic solution for sugarcane plantation. So this is work that we started around 2016, so it's around 4 years old. So I'm like just going to give you an overview and how much we had been achieving so far. But one of the interesting things on agriculture, and contrary to our expectation, is that with the introduction of mechanization, the yield per hectare goes down. And that's quite surprising. So we can plant much larger areas with less people. But on the other side, when we look to the yield per hectare, it typically goes down. So this is the case here showing for both Brazil and Australia, that are large producers of sugarcane, that actually when you introduce mechanization, the yield goes down. So the question is, we try to understand why this is happening, and there are many reasons for that. But one of the reasons that presently we have a much lower yield per hectare is that sugarcane is grass from Asia, that when you plant it, a new field, you normally take 1 hectare and you can plant 8 new hectares. But after you did mechanization, what you see is that 1 hectare can plant only 4 new hectares. So there is like almost a 50% drop on the new plants to grow. So we need to try to understand that. And one of the things, or the goal, is that if we could use robotics in this particular case, what we could do is try to select the damaged billets and send them for the mills to produce sugar, while the non-damaged ones we would use to plant. So in the old times, when you had things done manually, you have a man cutting the sugarcane stalk and planting it, the whole thing, into the furrow. But nowadays, with big machines, we cut them in smaller pieces, in billets, that damage the billets. And therefore, when you put them in the ground, bacteria start to penetrate these billets, and many of them do not grow. So what we have been doing for the last 4 years is like collaborating with different groups at the U.S. Department of Agriculture, where they have all the facilities, all the land that is needed for us to be running our experiments. And here is us, like, taking advantage of their equipment to collect some billets in Louisiana, in the south of the U.S., where we collect them, going through the different stages of the growth. And then what we did is like, to try to understand what was the problem. So we got several of the experts from the USDA to look at the billets and try to decide which billets might have a good chance of growing and which ones not. and we segregated them in the different positions. And following that, we use computer vision, both in outdoors as well as in indoors conditions, to try to understand the different damages that the billets were exposed to. We also did plant all these billets, so we could try to get a sense if the experts were correct or not, because perhaps the experts were telling us something that was not proper. So here are examples of the different billets, and just to show you how they can be, for example, have a big crack, or they can have the edges being smashed. And those will have a very small likelihood of growing. So we had classified multiple types of billets and multiple types of damages. And what we have seen after planting is that indeed the experts were correct. When we count how much it grows, only 7% of the billets that had any damage actually produce shoots, they grow. While the majority of them, the ones that are good ones that were considered to be good, only 50% of them did grow. Now, we use then computer vision, and this is the work primarily done by some of the colleagues in the lab, particularly Moisés, Alencastre, Miranda. And what we do on this using traditional algorithm is to try to classify the different phases and the different damages that we observe. So we go from detection orientation to detection of where is the ring, because there is a ring in the sugarcane, and next to that ring you see an eye, and that's from where the new shoots would be growing. And then after that we go and detect the different types of damages that we might be observing. And following that, we try to segregate the two. So this is an old video that showing more the work that we did 3 years ago, just summarizing what I had mentioned of the concept of using computer vision to segregate the device, the billets. And these are very simple first prototype of the machinery that we designed it to pick up the billets out of the wagons. Here is like a relatively just still alpha prototype that later was deployed in the field, but then put it inside a space where the computer vision would then identify the good and the bad billets, and then send the damaged ones to be processed into the mills for sugar, not wait and put them in the ground. The other thing that we also did is that the size of the billets is quite arbitrary. So we wanted to understand how big the billets need to be growing. So we also designed a cutter to try to cut the billets close to the ring, even in small pieces, so we could send the remaining to the mill to produce even further sugar. Now, that was done for one variety, and there are hundreds of varieties of sugarcane. So what we wanted to do is not to repeat the same process for each of the varieties, but also to try to expand that with a relatively automatic system for different varieties, to try to do the same thing without having to go through the laborious process of selecting, classifying, and going through the traditional algorithms. So here we did not only, while we did the traditional algorithm with one class of billets, we went further and took two other classes of billets. And again, here we saw how many would grow of the damaged ones and which ones, apologize. Here first, I'm like just saying when we take a wagon, how many are classified as damaged and how many are classified as good ones. So you can see that roughly 50% of the billets have been damaged by the machinery that are harvesting them. And then we go further and look to how many of them we can detect using the traditional algorithms to see if we can improve the selection criteria. Now, after we train it with the classical algorithm, we extended that, trying different networks, different nets, like AlexNet, GoogleNet, the ResNet, to try to see if we could, like, use deep learning and transfer learning to extend to different types of varieties. And we were able to do that. Here we are showing one slide where the blue represent the damaged one. So we are able to identify with a classical algorithm, train it with this type of billet. We are able to identify almost 90% of the damaged ones. And when we use different, the algorithms using deep learning, we can almost obtain the same thing. Without much of training. Actually, we only use 64 billets of the new varieties to train the machinery and then perform the selection. And one of the interesting things is that we were not being very good because we biased the classical algorithm because we have high quantities. Our goal was primarily to reduce the number of damaged ones. But because we biased the algorithm, the number of good ones that we properly identified was relatively small. But when we use the deep learning and the transfer learning, we are able not only to identify quite well the good billet, the bad billets, but also we can identify quite well the bad billets. And that leads to significant improvements overall for the system. Now, I'm not going to talk much further, but we are also doing similar things with weeding. The goal here is to use robots to extract the weeds mechanically if possible, or spot spray only where there is the lead, instead of using this kind of systems where you essentially are just spraying the whole thing with herbicides. And when you go to different fields, you have a very large and very varied type of weeds, and they are not isolated. So they are actually very much, they are all varieties of grass. So it gets it very hard for you to identify those amid sugarcane that is a grass when they are growing. So this was one of the areas. The other area that I would like also to call attention beyond the agriculture side that we have been working is also on this area of digital transformation. And here what we have been doing is trying to work with different industries. So I'm going to show here an example of what we are doing with excavators, where it takes between 3 to 5 years for you to get a good operator of like this kind of large machineries. But it's not very, there is no particular course that try to educate them on how to do this. So here what we have been developing is simulators that try to understand what the expert operator is doing, and then try to build a kind of a translator that would let a naive operator of an excavator like myself perform at closer to the level of the expert operator. So we had, like, similar to what we did with rehabilitation robotics, we have created a whole set of different environments and games that we use for training the naive operators, and also a whole set of evaluations that we use both for the naive as well as the expert operators to try to build this translator. Here is just showing a few of the environments that we build for training. Here, if we go to the evaluation, the kinds of things that we are trying to implement are very simple, basic, old-fashioned psychophysics type. So we would look to how long it takes for example, an expert or a naive operator and how they would do to feel, for example, to feel like, you know, the pipe of different sizes. How long and what is the procedure? The same thing for them to excavate and fill trenches. So we created a whole set of different evaluation tools that then we use to train them. Let me show you here one example. We have multiple screens, but here I'm just showing the top 2 screens of our simulator. Just showing here the test of filling the pipes. And this is one of my colleagues, so it's not what you would call an expert operator, but just showing how we have been doing this. And it keeps going from one task to the other one. But in addition to use the traditional joysticks, we have also been developing haptic interfaces. So not only they could perform the task using the traditional joystick, but they could also use some of the haptic interfaces that we have developed, so then the operator could also try to feel a little on these very large machines what he's doing down ahead of him. Here is just showing a little about the whole setup that we had developed. We use primarily Unity 3D for our visual simulator, and then we use the traditional real-time. I wouldn't say traditional, it's traditional for us. It's just the same real-time operating system in Ubuntu Xenomai to control more the haptic devices. This is again part of our goal, but when we are developing this type of excavators, we want to have a kind of a reasonable digital twin. So we also go quite frequently to the field to get response of the devices and then try to replicate the response in a way that makes the simulation look and feel close to real. So that's just showing different responses here of the actual excavator here in blue, and then like depending on the different models that we use, that we can replicate reasonably well for our goals, that is to give the same type of sensation for the operator in the digital twin of how they would feel if they were performing the task. So let's see here, just showing like the kind of information that you are able to collect. Like here is the operator filling the pipes and different movements to collect and fill the pipes. In this case, very similar to the same type of games that we had used in rehabilitation robotics, but with a different goal. We also had created, and we used the same data bank framework to analyze the data, similar to what we had developed also for rehabilitation robotics. So it's quite interesting to see how we can take advantage of tools that we have developed in one space and now be applying in a very different space. Literally, like, you know, going from interacting with very frail elderly, old individuals, to very heavy machinery, but we can use the same kind of basic tools that were developed in one space to another one to see how we can separate and see things as simple as, like, you know, asking somebody to fill the pipes and then asking them to perform that while doing a dual task, and see that you can see smaller differences. And those are very measurable, even in expert operators. So I hope I gave an overview of what we do. Not only, of course, we continue to push very heavily the rehabilitation robotic space, but also we have been pushing other areas in agricultural robotics, and also in the creation of these digital twins and translators. So those are the three areas that the team, pretty much a third of each of the people that I show had been working in different directions. So I'll stop here and get the next 5 minutes, if my clock is right, to give opportunities for questions.
Thank you very much for the very interesting talk. So if there are any questions from the audience.
Matteo, if I may.
Yeah, please, Andrea.
Hi, Igor, Andrea Davella here. I don't know. I apologize. I have a relatively weak connection. I don't know if you can hear me well.
I can.
But okay, great. Hi, Igor. So just curious about the concept of translator. Can you, in the second part of your talk, do you mean creating a training situation in which the naive can more rapidly get the level of performance of the expert, or actually modifying somehow the effect of the naive sort of commands to the excavator to improve the performance? It's not clear to me what's behind this concept, but it looks very promising and interesting. Thank you.
So you pointed to the two aspects of the project, for the initial phase and the second phase. So the first phase of the project, the goal is to transform the commands of the naive operators into commands that are closer to the commands of the expert operator. So that's not a training tool. This is actually a translator that would look to some of the aspects and try to modify them in ways that would make them be closer to what the expert is performing. At the same time, we would like, in the second part of the process of the project, try to determine if we can train, that we still can train the person. Because of course, those are contradictory aspects. So if you use a GPS to drive you, as you know, to any place in the world, it won't make me more able to drive by myself there the next time. So the goals here is to try to understand in the second phase how to balance the translation aspect of the algorithm, that is allowing them to perform perhaps closer to the expert, to try to use that and also train them. The second part we haven't started yet. So in the second part of the study would also to see if we can reduce the kind of feedbacks and try to also observe if we can also be doing training, perhaps at a slower pace. Or maybe the person would take a longer period to get to that level without that assistant. But the goal is to try to do both. Phase one, which is most interest for the industry, is to make this smart translator. And phase two is to make also the training tool.
Thank you. Yeah.
Yeah, there is another question from Jay.
Hi. So can I get a little more clarification on the the human assistance tools, it's unclear to me if you're actually somehow mechatronically taking control of the excavator and implementing some sort of autonomy or virtual fixtures, or if this is purely a visual guidance mode in some sort of virtual reality or augmented reality where you're giving them targets that they should hit on their own, but you're not taking any control of the actual excavator. Which of the two is it?
So in the translator, when the people are being evaluated, we are not taking actual control. So the goal is like just to try to identify what people do, the experts, and what the naive operators do in the visual. And I have to say, we have two environments. We also have, for example, toy devices. We have a kind of a sandbox where we have a miniature toy excavator. So in some cases, we are using the virtual environment, the simulator, but sometimes we also show the toy excavator to try to understand if our digital twin is closer to what you might call one step closer to the actual excavator. So that was, I'm sorry, I took like a side commentary that, but going back to your question, when we are doing the evaluations, we are not taking control. The goal is after we build the translator, we will kind of nudge the commands of the excavator towards what the expert would be doing. So it would be like, you imagine when you are flying a high speed combat aircraft, the pilot is not actually controlling the device. He's not controlling the airplane because the airplane is unstable. If he would be, but you would have like a control between the pilot and the actual airplane. So that's the ultimate goal for the industry. And we are trying to apply this for all very heavy equipment. So I show here excavators, but we have been talking with other groups that make very large pieces of equipment because it's the same kind of aspect. People get trained on the job. They really don't know how to train the operators. And this is a great opportunity for us to make this kind of digital transformation, not making it fully autonomous, but just trying to add some interface between the operator and the device.
Okay. So let thank again. Yes, another question. Yep.
Yeah. No, I was drawn into this by the last comment. I found the presentations very interesting, and this topic of not going for full autonomy, but rather working on the interface with a human is something that we are. It's basically our guideline in much of the work we are doing today. So very much in line and interested with this. So do you think that there is do you think that there is something the machine can learn from the human also? You have shown the other way around, right? The human learns, while the machine at the beginning helps and the human learns. But is it also possible that the machine learns to do things from the human?
So I'm going to here switch hats and talk a little about rehabilitation. So when we are delivering rehabilitation, we have two different ways that we have explored, and we are trying to understand how to go from one extreme to the other. You can have one case when the person gets entrained to the machine. So I'm going to give an example. We have developed like an ankle bot to assist people to walk. And in that particular case, if we try to apply the right stimulus, we see that the people, the patients and healthy subjects, they kind of track, they get entrained by the device if the perturbation, the assistance doesn't happen too far from the actual point. The other extreme that we also had been looking is the other way around, when we are trying to have the device guess what the person wants to do and provide the assistance at the right moment. So if we think on this, we are going from the two extremes. One where we are saying, I'm going to assist the human, but the human has to be the part that adapts to the system. And the second one where we are trying to have the device be smart enough to give the assistant at the right moment. And I think even more interesting than these two is how to transition between one extreme to the other, which is what we are trying to do also in this heavy equipment aspect, when we are trying to see how to make the ability to train the person at the same time that we are assisting them. And I don't know how to do this in heavy equipment yet, but in rehabilitation robotics, it's much easier to play this kind of games.
Yeah, that's interesting. If I have time, can I make a second question? Matteo? Oftentimes when you train neural nets, and you want to do something that it is you do not have data, then you create data by simulation, basically, and then it comes the problem that reality is not a simulation, and then the transfer. So how does it work with humans? So you train the humans on a virtual reality environment. How does it translate this accumulated knowledge when you switch to the real world?
So I don't know. What we do know is that that's why we brought the toy excavator. While I don't have the ability to have the real world and do the real tasks, but I have an ability to have a mid-step. So you can get this, in the case of the excavator, you can get like pretty big toys for very low cost that you can then use them in a kind of a sandbox to see if things make a little more real sense in the real world. But of course, the toy excavator is not the real thing, but it's one step closer. It's also hydraulic. It's like, you know, has a lot of things in common. So we try to make this intermediate step exactly because of your point. If that would actually go all the way to the real excavator, I don't yet know. Okay.
Thank you very much. Yeah, that will be interesting. I will look forward to reading your results.
Thank you.
Okay, so thank again, Dr. Krebs, for your presentation. So let's move now to the next talk. And the next talk will be by Dr. Verschuren. He is a research professor with the Catalan Institute of Advanced Studies and director of the Synthetic Perceptive, Emotive and Cognitive Systems Laboratory in Barcelona. And his scientific aim is to develop a unified theory of mind and brain and to validate this theory using empirical and synthetic methods and by applying it to technologies that support and advance the human condition. And in his talk, he will present some of the research outcomes on his theory. And his talk is entitled The Volitional Brain in Action. And thank you very much for having accepted this invitation. And please, the stage is yours.
All right. Great. Okay, apparently I have to accept things now to share my screen. Okay. All right. Do you see? Yep, we see something. All right, here we go. Do you see something that says the volitional brain in action?
No.
No yet.
Okay, I did share my screen. See something now?
No.
Okay, one sec. Maybe you have to restart Teams, so which I'm going to do now.
Okay. Now we can see the presentation, but we cannot hear you.
All right, now you should hear me and you should see something.
Yeah, perfect.
All right, I'm sorry for that, but
no problem.
Teams wanted permissions over stuff. Okay, the volitional brain in action. What I would like to talk about is really our idea of living machines, which is how can our understanding of biological machines, such as ourselves, inform the construction of artificial machines, and how can that construction in turn inform our understanding of ourselves and in particular the brain. So for that, I want to look at specific aspects of motor learning in the brain. I want to look at the brain as a control architecture. And I will show you how some of the basic principles we extracted in these studies have shown to have great value in the clinical application in stroke rehabilitation. Okay, we also have an annual conference, Living Machines. We have a handbook on living machines. If you have an interest, join us now, end of July. It's an online conference where we deal with this sort of merging of our understanding of biology and the construction of synthetic biomimetic machines. Okay, of course, the work is done by a whole team of people I'm just part of, supported by many different European projects in a range of areas. So we have projects that touch upon collective robotics and hybrid human-robot teams and interaction. We have projects on the brain, cloud infrastructure for brain data and the visualization of brain-related big data. And then we have other projects that look more specifically at issues like how can we understand navigation from a biological perspective, or how can we build better, let's say, exoskeletons for rehabilitation based on understanding of biology and cognitive architectures. So overall, the outlook we have, and this summarized with what I mentioned earlier, here we look at the human brain. I will say a few more things about it later. We build theories of that brain, about which we'll talk as well. We validate the theory on artifacts like robots. Here we have a motor learning system. But then these principles go back to the clinic. So in explaining the brain, we make predictions, but we also then validate our theories and hypotheses about the brain by exercising forms of control. And repairing the brain is such a form of control. But that, of course, returns data to the basic science exercise of understanding how this brain works. So this is really the loop in which we try to reside. So how do we see with the brain again? So that means the fundamental challenge for us is how do we link now this structure of the brain, the physical structure, the flesh, to its functions, or if you want, psyche. We start by considering that the brain is the product of evolution, so that means there's not necessarily an ingenious engineer behind it, but rather it is an ongoing experiment performed with the basic principles of evolution. And there in particular, around the Cambrian explosion of about 560 million years ago, all the life forms we know today, all the body plans we know today, together with their brains, were essentially generated. So what we take away from this evolutionary perspective, this comparative perspective, is that we should maybe first think about brains as encapsulating common design principles. So this is our starting point, and there's a lot of literature that would also suggest that even across vertebrates and invertebrates, we can still find common principles in which, for instance, perception works, or memory, or action control. And these similarities, and I indicate the paper at the lower left corner by Nick Strausfeld and Frank Hirth, for instance, these homologs can be found both also at an anatomical and even at a gene expression level, right? So the outlook for us is, what are these common principles that all these brains share, as opposed to saying like, well, each brain is a unique design. So brains then, in this evolutionary perspective, evolved because they supported survival. And following Claude Bernard and Ivan Pavlov, we commit ourselves to this idea that the main success of the brains that survive is their ability to control action in the real world. So if we look at this example, at the top we see a capucine monkey who are extremely expert in opening nuts by hitting them with rocks. They have also forms of imitation learning where they observe each other, how they perform these tasks. And this is done by tiny brains, smaller than our own. On the left-hand side, you see the human brain as visualized with the tool we built called BrainCube, which we also use in the clinic for neurosurgery and epilepsy use cases, which weighs about 1,500 grams. But it's built by about 90 billion neurons, and in the middle we see an example of what such a neuron might look like, in this case in the cat visual cortex, so that's in the back of the brain, where in red we see the dendrite, the input, and in gray with the yellow dots we see the axon, the output. So with 90 billion of these elements glued together, but if you further zoom in, and you see this here on the right-hand side, here we see a representation of a single synapse, so a single one of these little dots here, that in itself is again a whole universe of complexity that people try to unravel. So what we're looking at is a multi-scale system where we have different levels, different spatial temporal levels at which control systems and regulatory mechanisms engage. And this, in the end, all operates, in the human case, at an energy budget of about 20 watts. So if we now look at this mystery of the brain, and we still don't know how it works, we commit ourselves to this assumption that it's there to control action, then we have to say, okay, but then what are the objective functions that would underlie the optimization of action, and or how? And what we propose here is that these are essentially four in the engagement with the physical world, which is motivation, why, objects in the world that pertain to this motivation, which is what, where, spatial structure of the task and the self-localization within this task, and then when, which is the question of the dynamics of matching the dynamics of the embodied agent to that of the world, or we call this also H4W. So then how do we map that back to the brain? Well, this is the theoretical framework that we developed for that, and I'm going to highlight one aspect in that later on, but this is to give you a little bit the overview. So I look at the brain as a layered control structure, where at the bottom level we have very strongly prior specification of sensory motor reflexes or stereotype behaviors, where states of the world, for instance processed by the superior colliculus, you see here in blue, are mapped in an automatic way to structures for action, like the central gray area you see here in green, along the fourth ventricle, an area dedicated to stereotype behaviors, with the mediation of structures that encode states of self, like the hypothalamus. That might tell you about, let's say, oxygen depletion, CO2 levels, glucose levels, and so on. So at this level of control, this reactive control level, we already see a triad of interactions between states of the world, the states of self, and those of action. Now, in itself, these control systems that are fully predefined and strongly fully dependent, fully defined by evolutionary processes, if you would decorticate an animal, like a hamster, for instance, it would only operate with these structures and they can still survive. They would take care of their young, they would feed themselves, and so on. So these are very sophisticated control systems. They cannot just deal with, let's say, the unpredictability of the world. They cannot know about states of the world that are not genetically predefined. So for that, we need to rely on what I call the adaptive layer, where we have to solve a fundamental problem that reinforcement learning only now starts to address in deep reinforcement learning, which is we have to acquire the state space on which we have to build our policies. So for that, we look at, in particular, the temporal lobe in the human cortex, in the human brain, in which we also find the hippocampus, central memory structure, we're not going to talk about today, and the amygdala here in red, and the nucleus accumbens also in red. And in green, we see the cerebellum, which is strongly involved in fine-tuning and shaping the discrete actions that the reactive control layer generates, as for instance in the form of classical conditioning. This is a structure we're going to look at in a bit more detail later on. So what we're saying, on top of the reactive controllers, we have subsystems that start to identify states of the world that pertain to relevant events, to the self, and that help you to shape your actions in response. However, this system is only operating in a very restricted spatial temporal window. As in classical conditioning is very effective in most cases in time windows of up to about 1 second, and then the system will just give up. The only exception is if you look at food poisoning related conditioning, where you can have longer time windows of hours, but it is an exception to that rule. So if we now want to operate in a broader spatial temporal window driven by the distal features in the world, we have to move to other structures that can really acquire policies that are more goal-oriented and driven by reward optimization. And that brings us to the contextual layer, where we see more frontal cortical areas engaging, in particular in the prefrontal cortex, where we very strongly see states of the world represented, of a task. In red here we see again states of the self in the orbital frontal cortex, so just above the orbits of the eye and the insula, really deep inside the frontal cortex. And then we have again structures dedicated to action in green, which is the supplementary motor area, and then which is very much a gateway towards initiating action, and then the premotor and primary motor areas that will actually trigger these actions. So in this way, we can think of the brain as a layered control architecture where every layer is contributing specific functionality to the system. But the question is, of course, how do you regulate across these different control systems? And there, how we can think of this is that what the brain is trying to do is not necessarily to be optimal with respect to one of these levels of control, but it's always trying to optimize a trade-off boundary where on the one hand it has to be robust against perturbation, that's the axis on the left-hand side, while on the other hand it also must deal with increasing complexity. But if there's a sudden catastrophic event, then in itself to contemplate the metaphysical significance of it might be less relevant than just to run away. So in that sense, survival that the brain sports is one of continuously shifting the configuration of these control systems along this trade-off boundary. And there are examples of this, because then we can look at how would that shifting be accomplished, right? What is the regulation that would take place there? And one example of that would be the role of neuromodulators. Neuromodulators are systems that depend on very relatively small nuclei in more ancient parts of the brain, so brainstem areas, that, however, project to many other parts of the brain where they have a huge impact in regulating the response properties of these target areas. One example is, for instance, the famous dopamine response to reward, right? So you see in the left upper corner, the response to a reward, an apple. You see a strong positive response. However, if this response becomes predictable, then you see, and that we see here in the middle panel on this side here, if the reward is delivered that is predictable, then this response is diminished. Rather, it's now shifted to the predictive stimulus, right? So this is a very primitive brain structure. So the dopamine neurons are located here. They project to many cortical and subcortical targets where they have a big impact on, for instance, how these systems learn. So this is an example of how you then exploit these regulatory features of dopamine systems, in this case, to fine-tune your controllers. However, if you lose these dopamine neurons, you will develop a disease, pathology such as Parkinson's disease, right? So that means these regulatory systems are on the one hand a constraint. If you lose them, you will lose function, and that might be fatal. On the other hand, they also deconstrain, because by virtue of this dopamine system, we are actually able to learn in an almost open-ended way in a goal-oriented fashion in any task. Or we might attain what Alan Newell would call general intelligence, right? Where anything can become a task. So the concept here is one where the brain is organized as a multi-layered control system, regulated by subsystems that are now imposing significant constraints on the one hand, but on the other hand, optimize the integration across these control layers. So we modeled this in a theory called distributed adaptive control. This is very much the outlook that we have on how brains operate. And we have also shown that this architecture, as I just described it to you, captures all of the extant AI approaches that are popular today, like deep Q learning, AlphaGo, and so on, all fits within that broader framework. They just look at smaller slivers of how these control systems could work. So, okay, that's nice. Now I told you a story about how I believe the brain works, and why would you believe that, right? So that means we have to now come from our explanation to testable predictions, because that's in the end what theories have to do. So let's look at the predictions we can provide now on subsystems in this broader story I just told you, right? So I want to look at this adaptive layer. So this was the layer here indicated in this brain, where we're going to look in particular in how adaptive motor responses are acquired. And in there, I think, are some really interesting observations that also tell us something about how we can construct more robust and optimal motor learning systems for robots. So the particular paradigm we look at is classical conditioning. You're familiar with that, right? There is a tone. The tone will be coupled with the delivery, in this human case, of an air puff. And with time, we will see that the brain will respond to this predictive cue by helping the eyelid to close. That is in a way that is well timed relative to this noxious stimulus, the air puff or the shock to the eyelid. So here it's indicated then in green, the area in which you might see a response to this predictive stimulus, the tone, so that's the conditioned response, while in blue you will see the area where you can measure the unconditioned response from the animal, which stays rather constant. But what you already can observe here, if we go down this graph, you see that over subsequent trials, this anticipatory response is shifting in time. But on the other hand, what we also see is that the unconditioned response remains active. So as if after learning, we have a compound response that is integrating the acquired component, an anticipatory component, with a predefined feedback component. And that is actually also the idea that Ivan Pavlov already formulated about this. about more than 100 years ago, where he said, look, this acquired response is actually replacing the predefined response. And this in itself became, and still is, a dominant way in which we think about motor learning, where we have a feedback controller here at the bottom of the figure. The feedback controller is trying to minimize an error between the signals it receives from the periphery and some set value. And by minimizing that error, it automatically controls the actions the system is emitting. Now, if you talk about an adaptive motor learning system, you would stack on top of this feedback controller a forward component that via an inverse model starts to generate motor commands in a feed-forward fashion, so driven now by the predictive cue. But what we also see in this standard model of motor control, that it leads to a replacement, as Ivan Pavlov also anticipated, which means the predictive response is fully replacing the feedback controller. Okay, so this is a consequence of this solution, and that also explains why in many engineering solutions we run these feedback control loops at very high frequencies, so that you can still adapt to, let's say, exceptions that are not caught by the forward loop. So let's see how the brain is actually solving this learning task. So here we can look at the cerebellum, the green part you see here at the back of this brain. Here you see a top view on the cerebellar surface. And we know that in this lobula H6, if you measure here in lobula H6, you will find responses of the primary cells, the Purkinje cells, that are highly correlated with the initiation of these acquired responses, like the acquired eye blink. We know these circuits very well already for decades. They're very, as they called, crystalline, right? They're very well-defined circuits that actually show no lateral interaction within the cerebellum itself. We have the predictive cues coming in over the what's called the pons and the climbing fibers, the mossy fibers targeting the granule cells here, and from there forming the parallel fibers that target these principal cells, the Purkinje cells up here. The Purkinje cells also targeted by the so-called climbing fibers that originate in a small nucleus in the brainstem called the inferior olive. The inferior olive oscillates spontaneously, but these oscillations are transiently disrupted by exceptions, such as, let's say, painful stimuli. So painful stimulus will lead to a very strong response in the inferior olive, which then is conveyed to these principal neurons via the climbing fibers. The climbing fibers converge with the parallel fibers, so the sound converges with the error signal. Learning takes place. Learning means, in this case, that these Purkinje cells will reduce their response probability, releasing the deep cerebellar nuclei from inhibition, triggering a response. This circuit is well known. However, if you model the circuit, so here we've been doing that rather extensively. So here we modeled the circuit, we put all the anatomy together, all the physiology, and you try to understand, okay, what are exactly the stability properties of this learning system? Under what conditions does it really stabilize learning by the change in the synaptic efficacies and so on? And we tested this model in different ways. On the one hand, we built a neuroprosthetic device with it. So we emulated this whole circuit on a silicon device, which we interfaced with these input and output structures in the cerebellum to show, and I showed it in the plot on the right-hand side, that we could replace this cerebellar circuit in this eye blink conditioning task. So in green on the left column, you see the sound cues that are being triggered and our detections of these sound cues in the pons, so the input structure to the cerebellum. Then you see in dark blue in the fourth column, when we trigger the painful stimulus or the air puff, and in red and pink, you see the development of this conditioned response, right? And what we showed in these experiments that we could emulate, with our emulation of the circuit, we could fully replace the learning capability once that circuit was lesioned in the cerebellum. So then we thought, okay, we're on the right track. It all makes sense. Replacement is fantastic. So let's now start to vary the perturbations on this model by putting it on a robot. And we're going to do a robot version of eye-blink conditioning, where the robot is detecting, if you want, the virtual sound cue, which are these green bars, which it now predicts the collision. It collides with this virtual wall in this mixed reality environment. And in that way, you see the response of the model at the lower left side of the figure. So we do many trials of this kind to just see, okay, what are the stability properties of this learning system? And that's demonstrated here. You see we detect the predictive cue, the green cue. Then we have an acquired response in white, followed by also a compound with the unconditioned response in red. Now, this became relevant. So what we see, and I'll show it here in the middle, what we kept on observing in this robot implementation is that there was never a complete replacement of the conditioned or unconditioned response by the conditioned response, as Ivan Pavlov already had told us, and also as Kawato and others had advocated as the dominant view on motor learning. We just couldn't get it out of the model. And that raised the important question whether in the cerebellum this replacement actually really happens. Is the brain really replacing the feedback controller with a feed-forward controller or not? So that then became the next question that we had to answer, and we compared now two alternative models. On the left-hand side, you have the standard feedback error learning model of Kawato, and also Ivan Pavlov if you want, where a forward controller is generating via an inverse model motor commands, replacing the feedback controller. While on the right-hand side, we took an alternative interpretation that's more consistent with the data we obtained, which is, well, actually, the feedback controller remains active, but the forward controllers that are responding to the predictive cue are not via an inverse model generating action commands. They are basically generating and time shifting an error signal to still drive the feedback controller. The advantage would be that in that way, you still can capitalize on all the features of your feedback controller, its robustness, its speed, while in the meantime fine-tuning it to new features in the task space. We took a postural control task as our example. We know, and on the right-hand side, you see some of this data, we know that humans with lesions to the cerebellum cannot adjust their posture in an anticipatory way to forces that they are exposed to. So in that sense, it seemed a good paradigm to look at from this perspective of our cerebellar model. So we do a simple pole balancing version of this, where we compare on the top, you see the performance of the sensory prediction-based model, where we learn to predict error signals. At the bottom, you see the standard feedback error learning model, where we replace the feedback control. And in case of collisions, they both work equally well. At the left-hand side, you see the error that we get, the average error we get after learning of these two systems. Now we test these systems again in catch trials. So now things become more interesting, because we start to now generate the cue that says an impact is coming, but there's no impact. So we start to look at how robust is the system against the variability you might encounter in the world. And there an important difference now occurs, where you see that feedback error learning, the standard model, essentially fails in the case of catch trials and exceptions, which we solve by running feedback loops very fast, very quickly, at high frequency, while the prediction-based, perceptual prediction-based model performs really well. So what we just therefore show with these experiments, starting with our first robot observations, robot-based observations, is that probably what the cerebellum does is not necessarily feedback error learning, as shown to the left, but probably it uses something like a counterfactual error. It is generating a counterfactual error signal to predict upcoming errors and engage feedback control. So we tested here also on a real robot, on the perturbator, which confirmed these results. And then the question, of course, becomes, okay, is this consistent with how the brain operates? So in that sense, we would like to see whether this explanation we now give of motor learning as it is controlled by the cerebellum is consistent with the data we can get from that system in physiology and anatomy. Because now what we're saying is not only that as we move up our control hierarchy, where we start to virtualize task space, we also generate virtualized error signals that again move downwards into this control hierarchy. So for that, the question became whether there's any evidence that systems in the frontal cortex, so on the right upper hand side of the figure, yeah, this is a bit of a messy figure, but it's just a bit an illustration of the core concept. Is there any evidence in the brain that there's an internally generated error signal that would travel from frontal cortical areas, because that's where this virtualization needs to happen, down to the inferior olive that generates the error signals for the cerebellum? We know that the cerebellum receives a peripheral error. That's a painful stimulus or an actual error. But whether there's this internal error signal, we just don't know. Now, Chris DeZeo is one of the leading physiologists on the cerebellum. He already has been describing a very interesting circuit in the brain, the mammalian brain, on the top left of this figure, where he shows that actually the cerebellum is in a closed loop with the frontal cortex over the thalamus, right? So on the one hand, the cerebellum, when it triggers actions, is not only talking to the periphery, controlling the skeletal muscle system, there's also a signal traveling forward in the brain to frontal cortical areas. But from this frontal cortical area, there's also a signal traveling back via the mesoddiencephalic junction, indicated in this figure, that builds then a collateral onto the inferior olive. So there's an anatomical pathway that could actually support this new interpretation of motor learning. But when I talked about this with Chris for the first time, he was actually very pleased because he was having a dilemma, and that's shown on the lower left side of this figure, that here he is measuring in the cerebellum in a simple eye blink conditioning task, and he's looking at the signature of these error signals. And what Chris had observed is that after learning, he actually gets double error signals, right? So as you see on the left-hand side, there's a naive animal exposed to an error signal for the first time. But after learning, the signal doesn't disappear, as Ivan Pavlov predicted more than 100 years ago. Actually, you have a double error signal. So this double error signal is now exactly what we also observe in our model, as I show you at the right lower corner of this figure. This was our original observation in these robot experiments. So basically what this strongly suggests, and this is also something we're now pursuing more specifically, that the brain is conserving its feedback controllers, but it is manipulating them by just sending them fine-tuned and shaped error signals. And this was highly relevant for our understanding of the brain, because it turns out that if you look at the cerebellar structure, the core learning system for motor control, actually half of the neural real estate, half of the neurons in the principal neurons in the cerebellum are not projecting downwards towards the periphery. They project forward into the frontal cortex. And this has been a massive mystery, why that would be the case. This is actually the first concrete hypothesis that tries to make sense of this, right? To say, look, this recurrent interaction between frontal cortex and cerebellum is absolutely needed to generate the counterfactual control signals to fine-tune feedback control. Now I want to go for control, which is, okay, we have an explanation of motor learning. It looks promising, it looks plausible. It seems to be consistent with our understanding of the brain. But how can we find further validity for this? And for that, we went to the broken brain. And this here is an example of a brain post-mortem of a stroke patient, and this is in some sense the simplest deficit in the brain that we know. You just lost a bunch of neurons, and it's our idea that we must have impact on stroke rehabilitation, because if we don't succeed in the domain of stroke, you can forget having any impact in more complex and diffuse forms of brain lesions. So, okay, stroke is actually the main cause of the disability-adjusted life years in neurological disease. So in that sense, also it's an important challenge that we face, and also the incidence will only increase, of course, with the aging of the population. And on top of that, also now with COVID-19, we see worrisome also impacts on the brain that are stroke-like due to changes in blood coagulation and so on. So stroke, however, is not a simple challenge. Like here, I'm showing you the modalities on the left-hand side in which you can find symptoms, and these are now plotted across time. So there are symptoms that emerge very quickly in the acute post-acute phase, and while there are other symptoms that might occur very late. So it's a complex symptomatology that we have to deal with. So we built a virtual reality-based intervention system based on our theory. What does that exactly mean? Well, our theory predicts that what the brain really cares about are the different control systems affected by a stroke, and not so much this innervation and interaction with the periphery, right? So what matters more to the brain is to build new pathways to generate and control the specific control pathways that are perturbed by the stroke, then necessarily focusing on improving innervation of muscles and effectors and so on. So in our case, we completely focus on the goal-oriented and embodied nature of interaction. That's why you see two arms on the screen. It's embodied. So we want this brain to take ownership over these arms in this case, and with these arms, that brain will perform tasks, and these tasks might follow certain rules and so on. So here you have a meta-analysis that we published last year. So here we look at over 250 patients that we treated with our system. In total, we treated more than 3,000 by now. And we are plotting here the impact on two standard clinical scales, Fugl-Meyer on the top and Kahai at the bottom. Fugl-Meyer looks more at muscle synergies, like what are the kinds of movements that you can make with your limbs, while Kahai is more a scale that is functional, like can you hold a cup, can you button a shirt, and so on. The colors in the plot indicate the period post-stroke, from acute, subacute to chronic and late chronic. We go from 3 weeks in the earliest group to 3 years post-stroke. And what we're plotting here is the change on these clinical scales per week of treatment with our system. And the treatment intensity is extremely low on purpose, because I want to understand the lower bound. So people get 20 minutes a day for 3 days a week over 3 weeks, which is really a very mild intervention schedule. And what we see that basically any period post-stroke, we have significant impact on these two clinical scales. And this is an effect we have now replicated very reliably over many studies. But let's now look how we capitalize on this new insight of counterfactual error. And for that, we want to look at one very specific deficit you observe in stroke patients, which is called constraint or acquired non-use. Acquired non-use basically means that patients stop using their paretic arm, the arm affected by the stroke, and they start to use their healthy arm to take over its function. So if you do a reaching task here in virtual reality on the left-hand side, patients are asked to reach for a target in space, and you just plot the probability that people use their paretic limb or their healthy limb. You see a shift. There's a bias that the healthy limb starts to invade the workspace of the affected arm more and more. And this, of course, has knock-on effects, right? Because as a result, people use the arm less, there's less training with that arm, so the bias will become larger. So this will amplify deficit and lead to larger problems. Now, the standard intervention is called constraint-induced movement therapy by Ed Taub, proposed a few decades ago, where the sort of simple intuition was, well, if I just immobilize the healthy arm, I force the patient to use the paretic arm, then we might improve. It might go better. This is a very intense intervention. It's every day, many hours a day, 3 to 6 hours a day for many months, right? So it's very demanding. It's a very demanding therapy, driven by a simple intuition. But unfortunately, here's a recent study by Gert Kwakkel. If you compare it to standard treatment, there's no significant difference, right? So there's quite some controversy now about constraint-induced movement therapy, even though it's the standard across the world for neurorehabilitation, but actually its effectivity is not clear, even though the interventions are very high volume and high intensity, right? So it's not really working very well for all your patients. So we went another direction, and we were thinking, okay, if motor learning is driven by counterfactual errors, maybe what we're looking at in acquired non-use is a loss of controllability. And maybe if we just manipulate the error feedback to the brain, the counterfactual error to the brain, we can overcome this, right? So what we do is the following. Here you see Belen, the Rubio, who is the postdoc performing these experiments. Here's one of our tasks, right? So she's just reaching for these objects. She has to sort them in color-matched baskets. But what we now added to this, and that's illustrated on the right-hand side, we do intention-compatible movement amplification. So as your arm moves to the red dot, leaving an error between the target position and the hand position, in virtual reality, we reduce that error. So we amplify the hand movement in an intention-compatible way. Driven by the simple idea that came from our earlier experiments, that this would reduce error feedback, and therefore it will reduce the error that is manipulating or modulating the controllability of this end effector. So what we did here was 2 sessions with our patients. We have a dozen late chronic patients. We do 1 training session where we do not have any kind of amplification, that people just get comfortable and familiar with the training scenario. And then we do a 2nd session where there are 100 trials where we have amplification, right? So in purple, you see the baseline, the -6 I showed you earlier. In red, you see the bias in bimanual hand use after this intervention, where you see we have fully removed this bias. So again, hand use is fully symmetric after only 100 trials. It's about 10 minutes, now 15 minutes. And when we do the washout, so we stop the intervention, there's still a residual effect, right? So compared to having no impact with constraint-induced movement therapy after months of training, this looks extremely promising, and was also directly informed by basic principles we had extracted from our theories about how the brain deals with motor learning. So what I want to show, there are many other aspects of this, and maybe one to also highlight for you. If you look at the brain reorganization in these tasks, we also looked at that. So we had patients in this task not using this counterfactual amplification, but we just looked at the training task itself in virtual reality. That means we do not use exoskeletons. There's no external manipulation. These patients work with the system at home, but we did a guided brain mapping study where we used the transcranial magnetic stimulation to map out excitability from the motor cortex to the periphery. And there we looked at the innervation of the thumb muscle and the innervation of the lower arm to just see, okay, how does this change in this pure virtual reality driven training scenarios. And what we showed here, and I showed this the lower left corner of this figure, is that what I'm showing you here is the displacement of the cortical map after training. So we see significant displacement. But on the right-hand side, what's even more exciting to us is that this displacement is directly correlated with the functional recovery, right? But on top of that, what we observed is that even in these virtual reality training scenarios, the changes in excitability of the thumb muscle were significant, which is a big surprise because in some sense, we are not directly asking people to move their hands or fingers in the task, but they do imagine to grasp these objects, right? So this is a bit of a challenge also to those of you working on exoskeletons and orthosis, right? Because maybe we don't always need orthosis and direct support of the limbs to still improve their controllability by the brain. So with that, I'm not saying that we should forget about exoskeletons, orthosis, and so on. No, these are still very important tools we should use, but there's no single tool that would solve all the problems. It's more how we combine them. Okay. Okay. There are many other things we've done, including aphasia. So in the meantime, the rehabilitation gaming system, as we call it, has been covering all these domains of stroke deficits that you can observe. We have delivered. By now, this is an old plot, over 100,000 sessions, fully automated, no human intervention needed, over 3,000 patients, as I told you earlier. And what we're doing now, on the one hand, it's being commercialized by a company called Iodine that is now delivering this as a product that supports the full patient journey from the inpatient to the at-home phase. We're mapping it to other brain health challenges. In particular, we look at addiction, dementias, and mood disorders. So we really look at those deficits with the highest impact on the disability-adjusted life years. And in addition, what we're doing now, the interventions we built, which is more the lower left corner of this system, a big challenge we face there is still diagnostics and prognostics. So if you get a stroke patient, we can use different techniques like MRI to see where the lesion is, but that's still not enough to really have accurate predictions of where the patient will be 6 or 12 months further down the line and what kind of interventions and therapy they will need. So therefore, we are now linking sort of whole brain modeling techniques with patient data to optimize the intervention planning. And these are trials we're running right now in a number of hospitals across Europe. So in that sense, bringing together really basic neuroscience theory that we test in real world systems and robots to improve clinical interventions, and in that way also generate new insights and new data that we can incorporate in our theories. So thank you very much. It was a pleasure to be part of this jam session, and if you have any questions, I'm here to answer them.
Okay, thank you very much for the interesting talk. Is there any question from the audience? Yeah, so otherwise.
Yeah, I have one question that says, how about respecting time limits for presentations? Look, if you worry about time limits of talks, don't attend, because they don't care about learning.
But this is part of the spirit of the jam session. So. Okay. So I would have a question. So related to this very interesting model on the combination on the feed forward and the feedback component that the brain uses actually for body control. So I'm curious about the extension to stroke patients, because in that case there is, I think, also a limitation in terms of the feedback that can be obtained from sensory information during the interaction. So my question is that there could be the possibility in extending your model to stroke to understand which sensory part or sensory information could the loss of some of this information could have played a major role eventually in the sensory motor impairment of this kind of subjects.
Well, so one thing we are looking at is, on the one hand, you want to look at functional activities of daily living. So you don't necessarily want to look at the EMG level of what kind of interface you can build, but you need some exterior system that looks at overall functional effectivity of actions that the patient performs. For instance, in an important discussion is this whole idea about true recovery, right? Where you would say like, oh, any form of compensation is wrong and should be avoided. And this is, of course, something you can detect if you just take a very body-centered perspective on recovery. On the other hand, there are plenty of patients who with slight compensatory movements of the shoulder can basically accomplish very effective actions with their hands, right? Grasping, reaching, and so on. But that is something you're blind to if you take this very body-centered approach. So we're in one project, Rehype, where, for instance, we look at building cognitive architectures for exoskeletons that really will have this capability to assess overall functional success, if you want, of the user. In addition to, of course, this direct coupling with, let's say, EMG signal, more physiological signal. So I really think we have to go to more distal sensing that's more task-oriented in this case. This is, I think, our challenge.
Yeah, thank you very much for the nice answer. We get a question from the YouTube chat. Very interesting talk. Can you please explain how your theory could take into account intra-trial variability of movements?
Well, this is actually a really interesting issue we're looking at right now. So our idea is that the brain actually is purposefully generating movement variability. It's as if it has to sort of have a little warm-up period to start to engage all brain systems in order to then perform the action. So for instance, if you look at memory systems, this is the angle we take here, memory systems need sort of a minimum amount of energy to start to do their work and form memories. So what we believe now is that part of motor action that we now call uncontrolled variability is actually very purposefully playing this role of energizing all the controllers before you then engage. And actually it's intuitive, right? Because in many activities we perform, we don't go from zero to completed action. Often you see initial movements, and we see this as part of, if you want, a preparation phase of the whole brain to perform an action. So there's a reason for this variability. It's not an accident.
Okay. Thank you for your question, for your answer. I think we have... yeah.
Jake Abbott has a hand raised.
Jake is still is a new question?
No, that's okay. An old hand raised. I guess I have to manually take it down. Sorry.
Okay. So I think we have arrived at the first break of the session. So I would like to thank again Dr. Verschuren for his talk, and we will have a 15-minute break, and then we can continue with Jake Abbott's talk. So thank you very much.
Thank you. It was my pleasure. Thank you.
Thank you, Paul. It was excellent.
Thank you.
Will you send a copy of your slides?
Sure, yeah, no problem.
Matteo, are we collecting the slides? Is someone taking care of Manolo or Paolo?
Yeah, we can. Yeah, we can start. the sessions with the next talk. The next talk will be by Dr. Abbott, who is a professor in the Department of Mechanical Engineering at the University of Utah, a core member of the Robotics Center and the head of the Telerobotics Lab. And his research synthesizes topics from haptics to magnetic methods for application, ranging from medicine to microgravity. And Jake is a recipient of several international awards, including the ICRA Best Manipulation Paper Award, the Haptic Symposium Best Paper Award, and the ICRA Best Paper Award in Medical Robotics. And in his talk, which is entitled Exploiting the Imperfect Human for Improved Haptic Interaction, Jake will present some of the outcomes of his research, which targets the usage of simple techniques to improve a human user experience during haptic interaction by understanding and exploiting the imperfections in the human user sensing and processing abilities. So thank Jake for being part of these sessions, and the stage is yours.
Thanks a lot. Thanks for having me. Yeah, so when you asked me to give this talk, because I was part of a committee on haptics, I thought really what I wanted to do is just tell you guys about my newest results that deal with haptics and human-machine interaction. And I realized that the common thread of these newest results all have to do with trying to make systems, human-machine systems, be as good as they can by somehow looking at the imperfections in the human to either exploit those imperfections or just at least deal with the imperfections to make a system as good as we can. So all of the projects that I'm going to talk about are all either published in 2020 or they're not even published yet. And they all have this common theme, even though they kind of take different paths. So the first project is what I call a hybrid force moment breaking pulse, which is a new type of haptic illusion to increase the perceived hardness of virtual surfaces. This paper just barely came out this week, and it was done by my PhD student, Ashkan. And so here's the basic idea. When you're using a kind of traditional commercial kinesthetic haptic device to interact with virtual surfaces, you basically start with this building block of an impedance type environment. So you're going to penetrate some virtual environment. You're going to take that penetration distance and times it by a spring constant, and that gives you a force. And if you want to make surfaces feel hard, you can try and turn up that stiffness constant, but eventually the system will go unstable and you'll start to vibrate on the surface. And that doesn't feel realistic at all. So other people have worked on other types of event-based things like breaking pulses, where just during the actual first contact with the environment, you give a big force that does this dual purpose of slowing down the momentum of your hand, and also it adds high frequency content that's realistic. When you really tap a tool on a hard surface, you get this kind of ringing. But even if you do this sort of thing to make surfaces feel harder without turning up the stiffness, there's eventually a limit you reach due to the saturation of the device. You just can't get any harder. But my question was, can we push our devices, our commercial haptic devices, beyond what we think they're currently capable of? So let's consider this really simple. This haptic device is drawn in this kind of 90-degree configuration for a reason. So you're touching this virtual sphere, and there's a force being pressed upward from the virtual environment at the haptic interaction point. And if you look at this actual kinematics, only motor 2 is being used right now. So when motor 2 saturates, you're as hard as your surface can be. But if you look at if you think about this in sort of a quasi-static way, if you think about the reaction forces at the hand, your hand is experiencing both an equal and opposite reaction force, but also a reaction moment due to the moment arm of the tool handle. And so whenever you have touched an object with a tool in your life, you've experienced both this reaction force and reaction moment due to just a force. So our thought was, is there a way that we can somehow make use of this fact to make surfaces feel harder and take advantage of the fact that 5 of our 6 motors aren't even being used at all right now? So here's our basic idea. Let me switch back and forth really rapidly so you can just look at the image. So you see the basic idea is we're trying to increase the reaction moment at the hand without changing the reaction force at the hand. And the way we're going to do that is by using unused actuation capacity. So the notion here is you've already in your life had this applied moment or this reaction moment as part of a typical interaction. And our question is, if we increase that reaction moment, will that somehow make you feel like this surface is harder, even though it's a not physically realistic thing to do, because in reality, there's no applied moment? Will it feel strange? And at first we were wondering, in pilot testing, it seemed like this actually worked. And we were wondering, well, maybe we're just adding more high frequency content. And people already know that makes things feel harder. So we tried reversing the sign of the torque on motor 5. And we actually found that although it added the same amount of high frequency content, it actually made the surface feel softer. So we knew it wasn't just high frequency content, it was actually a type of haptic illusion. And I've given you in this drawing a very simple kinematic structure, but in the paper, we really describe how to think about this in general for a general configuration and a general haptic device. So we did a human subject study where we actually did 2 separate studies that were identical. Each had 10 subjects. The only difference was the question we asked. So we showed them 2 surfaces and we let them toggle between these 2 surfaces and tap back and forth between them until they believed either one was harder, that was the question, or on another group of people, which one felt more realistic if we're trying to simulate a hard surface, a hard metallic surface. And we wondered if this question could potentially bias their answer. In the results you see below, the pink boxes represent areas that are not statistically significantly different from random chance. So when we asked which surface feels harder, we found that by and large, the vast majority of people and the vast majority of trials believed our surface felt harder. And when we asked people which surface felt more realistic, also the supermajority of people said it feels more realistic. Although we did find one person who never chose, out of 20 trials, never chose our method and told us that it felt weird. So what we think we've discovered here is a new type of haptic illusion. And we actually think it's a quite robust illusion. If you look at other well-known haptic illusions, they have similar kind of robustness to what we're finding here. So this is a new way you could essentially add this to an existing haptic device to make surfaces feel harder with the same device, but it needs to be something you can sort of toggle on and off for people who are the ones who aren't fooled by this illusion. So let me move on to another project now, also aimed at making existing haptic devices as good as you can make them. So this is a project that's currently under review at Transactions on Haptics, and it was a project done by my student Ruisa Zhang. She's a great student who's actually actively looking for a postdoc right now. And so what we wanted to do is we wanted to improve the ability to render these sort of engineered surfaces with haptic devices. So if you have a commercial haptic device and you're trying to render a texture, and I'm talking about textures where there's a really rigorous pattern. So I've given you 4 examples here where there's like a single main frequency component that you feel. When you're doing this with a commercial haptic devices are running at 1 kilohertz. So that's a 1 millisecond update rate. And basically the 2 ways that people think to do this in the state of the art is you explicitly render the surfaces. So every little texture has an up and a down. But when you implement those methods, you find that there's aliasing effects, especially when you move your hand quickly over the surfaces, that make the surface feel unrealistic. Things kind of drop out on you. The other approaches are stochastic methods, and those work quite well for stochastic surfaces, let's call them. So this is like sandpaper and things that don't have a regular pattern. But if you try and use those methods on these regular engineered surfaces, they have a gritty, kind of noisy sensation that's not realistic of those engineered surfaces. So what we wanted to do is see if we could render these kind of surfaces better than commercially available. So when we start looking at the 1 kilohertz update rate of a haptic device, and we think about this 1 millisecond update period from your D to A card, we realize that if we only consider periods that are integer multiples of those 1 millisecond periods, we can actually span almost the entire frequency range that could be possibly generated if we think about the just noticeable difference in frequency discrimination. So humans, this is a well-known fact, that humans are not able to have sort of infinite resolution in their sensing capabilities. So if I'm giving you one frequency, I have to change that frequency by a fairly sizable amount before you can tell it's different from the other one. And if we look at, for example, the orange box here, this is the haptic just noticeable difference if we consider both even and odd multiples of these 1 millisecond periods. And you see that if we just consider those, we're well within the just noticeable difference. So basically, we could move from one integer period frequency to another without you telling that there's a discontinuity. So there's really no reason why you should ever have to render frequencies in between those integers. The only exception to that is in this small band between 333 hertz and 500 hertz. So we had to make an exception at 400 hertz. And so I'll talk about how we do that. So this is our basic idea. So if you're going to display frequencies to people, let's think about these purely temporally. So you're just holding the haptic device in your hand, and I'm going to play a frequency to your hand, almost like I would play music to your hand. And we actually do that sometimes, play them with audio files. So the way that we would do this, it's easy to display any even period frequency. You just implement it as a square wave. So you go high and then low, high and then low, as long as you're an even period, an even multiple of the 1 millisecond period. But what do we do about all of the other signals? So method 1, and this is a method that's basically a purely temporal method of kind of the state-of-the-art haptic grading method that came from Hong Tan's group. But what you do is you say, I have a frequency I want to play that you think of as a continuous time sinusoid, and then you're just sampling it discretely. So that's what we'll call method 1. Method 2, we can do a weighted mixing of the two neighboring even period signals. And this is essentially an extrapolation of a method that came out of Ed Colgate's group, but we're really applying it in a way that's not what they intended. But that's a method we tried. And then method 3, which is our proposed method, is basically what we do is we say, all right, we're only going to use these signals that are even multiple and odd multiples of the 1 millisecond, and we won't ever try and render anything in between, and we'll rely on human J and D. But if we want to do odd period signals, we have to do them in an asymmetric way. So for example, in this plot, what I'm showing you in the 4 columns, I'm showing you the desired vibration and then how methods 1, 2, and 3 would handle these. And in the top row, I'm showing you how we would handle even period, meaning even integer multiples of 1 millisecond. They all do it perfectly. The interesting thing happens when we think about odd periods. You actually see the aliasing effect happen in method T1, where the impulse up is stronger than the impulse down. And if you render this to your hand, you can actually, in addition to the pure vibration, you can actually feel a net force pushing you in one direction, which is undesirable. In method 2, where we're sharing these two frequencies, you actually see that there's sort of extra high frequency content. And so it's not surprising when that has an undesirable feel. And then with our method, what we've done is for the odd period signals, we choose the amplitudes of the two periods, of the two halves, to be such that the impulses are equal. So the area under the curves in the positive and negative direction are equal. I think for brevity, I'll move on past that. So that's the basic crux of the idea. And so we did a big human subject experiment that was just what I described. So you're holding a stylus in your hand and we're playing these frequencies to you. And how we play them is we play an even, odd, even cycle. So it's sort of like ba, ba, ba. And we play that to you in both methods. Ba, ba, ba. And maybe the other methods feels like ba, ba, ba. And we just ask people which one feels like a steady progression. And the evens feel perfect. It's only the odds that are different by method. And we do it with high intensity and low intensity vibrations in case that makes a difference. And we do it with headphones on and off in case there's a sound component in addition to the haptics. And basically what we find is that there's little differences between the experiments, but the overall takeaway is that at high frequencies, our method feels better than method 1. At low frequencies, our method feels better than method 2. And there's often an overlap of frequencies where our method feels better than both. There's no cases where the other methods feel better. So we think that this is a new way to play frequencies on a kinesthetic haptic device that's sort of the best way you could do it given the 1 kilohertz update rate. So then we applied this to an actual haptic grating. So now you have a real surface. It's a one-dimensional surface. And we're essentially implementing versions of method 1 and method 3 in this world. And all we do is it's completely free exploration. We ask people to just explore these two surfaces and tell us which one feels better. And it's very open-ended like that. And when we do that, we look at different kind of wavelengths of these features. And when we find that when the wavelength is very small, we find that our method is statistically significantly preferred over method 1. And if as the wavelength gets bigger, we find that that difference goes away. And that really agrees with the results from the static experiment I talked about earlier. So now I think we've found a new way, if you're implementing these sort of textures, a new way that you should think about doing that if you want to make it feel as good as it can feel. Now let me move on to Ruisa's other project. This is a work that was just recently presented at Haptic Symposium. And then we have a new paper that's under review, which is a sort of follow-on to the original paper. And that's also, it's all unpublished. And here what we're trying to do is dimensional reduction. So we're still looking at this vibrotactile display using a stylus, but it's a little different question. So if you think about the ways we can do vibrotactile display with a stylus, for example, one way you can do it is with a phantom omni like this. And so I'm literally commanding potentially a 3 degree of freedom force to the haptic interaction point. We can do it with 6 degree of freedom haptic devices. So I potentially could command up to 6 degrees of freedom of forces and torques to the haptic interaction point. Or we could do it like this example from this texture pad, where we literally attach a vibrotactile actuator to the stylus and then it vibrates. And so that will be in 1 specific degree of freedom. But all of these things, no matter what you do, it's well known that once your frequency gets above about 20 hertz, you can't distinguish the directions of these vibrations. So all you feel is vibration with an intensity. And so something is happening in your brain where you're essentially taking this, what's ultimately a 6 degree of freedom stimulus, and you're mapping it down to a 1 degree of freedom stimulus that's actually perceived by your brain via your hand. So our question is, can we really fully understand this problem and then exploit it? So, I mean, ultimately what we'd like to be able to do is for a given haptic device with a given configuration, sort of give the smallest possible actuation signal to give you a nice sense, a nice salient sensation. So the closest work that anyone's done to this is a work from Catherine Kuchenbecker's group, where they developed this method. It's now quite well known, called DFT 3-to-1. So in what happens in DFT 3-to-1 is it basically says you have these 3 orthogonal forcing directions, and I'm going to think about the accelerations that resulted from each of those. And then I'm basically going to add them together kind of using Pythagorean theorem. So it assumes that the 3 force directions are totally orthogonal to each other in the way they contribute with equal magnitudes of contribution. And it's been shown that this method works well for this case. It's unclear how you should extend this method to include applied torques, which is what we're interested in as well. So basically, our proposed method here is that we would use this basically positive semi-definite weighting matrix to weigh the force and torque inputs. Now, when you think of these forces and torques, these are each amplitudes of sinusoidal signals. all at the same frequency. And so this is our proposal, that we can actually couple these in a way where what you get out is a skin absorbed power, and it's a normalized function. So when this P tilde equals 1, that corresponds to the detection threshold. And then if you're less than 1, you can't feel it, and if you're more than 1, you feel it stronger than the detection threshold. And you actually would perceive these in a log 10 scale, which is known in the literature. So we already know from our previous studies that if we look at such a stylus and we excite it in these different directions, we have a sense across frequencies of what these kind of detection thresholds look like. So what we've never done is seen how they couple with each other. So we did this big experiment using this magnetic haptic device. So you're actually completely untethered from the haptic device, and we can command forces and torques. And we did 45 different combinations of forces and torques. So for example, if you look at, let's say, row 15, I'm giving a force in the x direction and a torque about the z-axis with everything else set to 0. So there's all these different configurations. We gather this big data set, and then we basically do a big optimization process in this logarithmic scale. And we find out that the coupling matrix for these is fairly simple, but more complicated than kind of a simple orthogonal assumption would make. So we see that, yes, the force in the y and force in the z components actually are equally weighted to each other, but the force in the x is slightly smaller, which is not what the DFT 3-to-1 method says. And there's also an orthogonal, a coupling component between the y and z components. That's also interesting. The torque components are very interesting. We see like very, very salient vibrations when you rotate the stylus about its axis compared to other rotations. And there's actually a coupling term between tau x and tau y. And if you sort of sit and visualize how a stylus would roll in your hand, it kind of makes sense, roll and slide, it kind of makes sense why that would happen. And when we take this model then and apply it to our entire 45 configuration, 12 subject data set, we see the model is doing a very good job of capturing this threshold detection behavior across configurations. There's still a lot of variation because you have 12 people and people are just different. So anytime you try and make a one-size-fits-all model, there's going to be variation left. But you can see the model is doing a good job of going kind of right down the middle in all of these configurations. And the model only requires as little as 4 parameters to fully specify the stylus. So the final project I want to talk about is quite different from the others. It's a new thing we've created called translational and rotational arrow cues, the track navigation method for manual alignment tasks. And this was done by my student, David Yusevich. So here's how image-guided surgery looks a lot of the time, if you don't know. So basically what happens is you have optical tracking markers on your instrument or your tool, and you have some sort of plan of where you want to put that tool. And you see that the surgeon is looking at a screen where there's a couple of different orthogonal views of where you want the tool to be and where the tool actually is. And his job is to sit and stare at these 3 orthogonal views and try and line up the tool in all 3 views. And that's a very common way to do things, and it's also a very frustrating way to do things. It's easy to get it roughly aligned. It's very hard to get it precisely aligned. So that method is called the triplanar display, and you can see here how we've set it up. It's very common. It's very frustrating. Another method that's used clinically is what we have called the site alignment method. There's different proprietary names, but basically you use one main view to sort of line up your target. It almost is like shooting a gun, to line up your site with a target site and move in and out. And then they give you an orthogonal view just to help you, but you actually don't look at the orthogonal view very often. In many cases, this method works much better than the triplanar display, but we still found it quite frustrating, and we thought we could do better. So we started looking at the human psychology literature of how humans perceive spatial motions. It's well known that if you try and visualize the rotation between an object in its current pose and its desired pose, there exists an angle and axis, a single angle axis you could rotate about efficiently, but people cannot visualize that at all. It's also well known that rotations and translations are what are known as separable in your brain. So you don't really do both at the same time. Once you're doing precision alignment, you switch back and forth between translations and rotations. I'm going to move on for time. So here's basically how the track method works. Rather than giving you multiple displays, we give you one primary display of a target pose, which you quickly align yourself with just in a very rapid gross alignment stage. And then once you're close, we give you one arrow cue at a time, and it's in the object's frame of reference, not in the world's frame of reference or an egocentric frame of reference. We give you one rotation cue to follow until we give you another rotation cue. And we find that this method lets you quickly converge on the desired pose. And we give you these alternate views just in case the arrows become obstructed. You only need maybe one or two alternate views. The thing that wasn't clear in the literature is how if we should give you 3 arrows at a time or 1 arrow at a time. We knew we weren't going to give you rotation and translation at the same time. And the literature isn't clear of which will be better. And the truth is they're very, very similar to each other. We see a small improvement in people's times if you only give them one thing to look at a time. And that kind of makes sense. We make the choice for you. It just sort of removes your cognitive burden. So now we only show one arrow at a time. And then we do a big experiment where we compare our track method to the triplanar display, to the side alignment method, all making sure to control for the size of the object. So you can see that the size of the target and handheld object are the same in all of our environments. And we separate our results by men and women because it's well known in the literature that men and women have different perceptions of different spatial awareness. And you could make a method that's potentially better for men, but not better for women, and vice versa. So what we find is that when we're doing 6-stop tasks, the track method is significantly faster for all cases for women, and it's faster than the triplanar display for men. And then when we consider 5-stop tasks, where you're trying to think of sort of a needle task, where it's not important the roll axis around the needle, you just have to do the 5 degrees of freedom, we find that the track method is much faster for both men and women compared to both methods. And I want you to notice these are on a log scale. So we're talking about with the track method, you can do very precise 6 degree of freedom and 5 degree of freedom alignment in sort of less than 10 seconds, where in the other methods, it can often take you multiple minutes to do such an alignment. That's my time, and that's all I have to talk about. I'm happy to take any questions.
Thank you very much, Jake, for the nice presentation. I would like to start with some questions of mine on this presentation. So the first one is related to the first topic you have presented. So the idea of adding some torque to increase the perceived stiffness of a virtual wall. So in this case, I think that you don't produce any, so you still respect the passivity condition of the interaction, right?
Yeah, I mean, all of these kind of contact-based events are sort of outside of the stability consideration, because what you do is you say, when I cross the wall, I'll give you this one-time event, but then I'm not going to allow you to get another such event either for some period of time, or what we did is we said you have to raise the tool, I think it was 3 millimeters above the surface before you can get one again. So it isn't something that can enter into an unstable loop. It's sort of a one-time injection of power. And it's unclear to me if we're actually respecting passivity. But I would say from the argument I just made, maybe that's not relevant.
Yeah, because
it certainly can't enter into an unstable mode.
Yeah, no, because in the end, yeah, the golden standard definition by Ed Colgate, the one of the constraint in the stiffness of the virtual wall is related to the passivity condition during the interaction. And basically with the torque, you probably inject some power in the system, so probably the passivity is violated in this case, but since it's only one contact event, I understand your point. So with this explanation, thank you.
Yeah, sure.
And the other question of mine is related. So it's interesting when you presented the dimensionality reduction in the vibration in the humans. So basically, I knew the things that humans cannot distinguish the directions of vibration, so you can provide just the intensity. But when you have shown the metrics with the coupling between exactly the force and the torque, so basically at a perceptual level, humans are not able to distinguish some combination of torque and force. So there it's a kind of new space of the perception, right? Is it right?
Yeah, I mean, it's so basically any force, any sort of 6 degree of freedom force torque that I play to the haptic interaction point of your stylus that results in that P tilde being equal to 1 will be right at the detection threshold. And then if you're above, so in log space, basically 0 is the detection threshold. And then if you're above 0, that's something that's stronger. And if you're below 0, that's something that you probably won't be able to feel. Yeah, so it's a new way of thinking about this. I mean, it's quite related to the work that Catherine Kuchenbecker's group has been doing for a while. Really, what we've done is we've added torque to it, and then we've thought that there might be these more off-diagonal terms. And so I think that's the real contribution, and sort of an acknowledgement that, and you can actually see if you look at this upper left block, what the DFT 3-to-1 method does is it says they say it's a diagonal matrix with the same number on all 3 diagonal elements. Mm-hmm. And when you look at this, you realize that actually would probably be a good approximation. So you can see why the DFT 3-to-1 method has been as successful as it has, because it's pretty close to the truth. But the truth is, we find for most frequencies that forces directed sort of wiggling along the stylus as opposed to orthogonal are a little weaker, and that's what we find here. And then apparently there's actually a forcing direction that's kind of more diagonal up and towards the person as they're holding the stylus in front of them that will feel the best. And then there's an orthogonal direction that will feel the weakest. Mm-hmm. So yeah, I think one of the really interesting things too was that it turns out that vibrating the stylus by rotating it about its axis is actually by far the best way to give a sensation. So if you're thinking, because I mean, look at the magnitude, we're talking, this number here is 2 orders of magnitude bigger than these numbers. And the cool thing about that is if you look at these haptic devices, think about if I'm going to use this haptic device, for example, to interact with a virtual environment, I'm probably not even ever using that 6th motor. It just doesn't get used in the rendering of the environment because you're commanding forces at the haptic interaction point. So you have this tiny little motor that's attached to your stylus in both of these devices that's almost never being used, and that's the motor you should be using to provide vibrotactile cues because it's so salient. And one of the reasons it's so salient is because the moment of inertia of the stylus in that direction is so small. So that sort of force, or that torque leads to very large angular accelerations because the moment of inertia is so small.
Yeah. Yeah, no, I like very much this investigation. I think it's definitely of value because it combines mathematical modeling with a very in-depth psychophysical motivation of this approach. So I think it's a very useful also for future design projects of haptic interfaces which target this specific haptic rendering. So yeah, very interesting work.
Thank you very much. I'm glad to hear that.
Okay, there is one a question by Manolo, and there one by Hermano later.
Yeah, very quick one. So first of all, thank you very much for your talk. Very interesting and exciting research. I think a very interesting also question for who is doing planning from robotics point of view in logistics and intralogistics is how to combine different actions. And in one of your slides, you pointed out that from your literature, when someone has to do precise placement, combines rotation and translations in sequence, not at the same time. Can you please comment a bit on that?
Yeah, I encourage you to read this paper by Jacob et al. From 1994. This idea of integrality and separability is very interesting. And Shuman Zai at University of Toronto a long time ago now did a bunch of experiments basically showing that these things actually happen. So they did a bunch of experiments where they used a 3D mouse, a space mouse, to control things, and you can actually see sort of, if you look at error in position and error in orientation, you can actually see that each one drops while the other one either stays constant or even rises a little. So you alternate back and forth. So you do this first kind of big movement where you move yourself where you want to be, and that happens holistically. And then once you're there, your brain thinks about translations and rotations, one after the other after the other. And he actually talks in that paper about a lot of different things that are integral and separable in our brains, and how that can lead to thinking about human input devices. That what you should do is, if things are integral, you should control them with a common device. And if they're separable, you should actually either toggle between devices or use two separate hands. It's a very interesting paper. Does that answer your question? Okay.
Okay, there is one additional question by Hermano, I guess.
So, very nice talk. I have a question about that matrix and just ask you if you had done anything combining this with, say, the stiffness of the joint. If that has, because I'm looking to the numbers and the coupling, and I'm thinking about a dart thrower movement. So I was curious if perhaps the stiffness of the particular joint or something would have an influence, and if you are considering that when you are looking to these results.
I suspect it will have an effect. So in this experiment, what you're seeing is the stylus is being held in front of the person like this, and it's just using what we said, just a comfortable grasp. You know, they were sitting there for a half an hour, and we just said, hold it kind of comfortably like you would hold a pen. We for sure know that when we think about converting these forces and torques to their equivalent accelerations, we're not just talking about the inertia of the stylus, but we're talking about also the inertia of the limb and the tissue. So it's the combined inertia. When this stylus has to move up and down, even by microns, it's moving tissue with it and limb with it potentially. My suspicion is that if people hold the tool really tight, these numbers will change. And so that's an increase in stiffness. I'm actually not so sure when you say joints, I hope we're talking about joints of like the fingers. I'm not so sure that like, adjusting the stiffness of your whole arm would make a difference. But I do agree. It's complicated. And so I think all we've done here is said what this kind of coupling relationship is and the relative magnitudes of these things. But as it says in this second bullet, our current work is actually trying to go the next step and say, okay, so if this is the coupling relationship, how do we find these numbers or model these numbers across different styluses and across different frequencies? And it turns out we have been able to develop quite accurate models where you can basically give us your stylus properties, and then we can tell you what these numbers in this matrix should be. But the truth is, if someone really squeezes down hard on the stylus, I think the numbers will all be wrong by some amount. I mean, it's a very insightful question.
Thank you.
Okay, so let's thank again Jake for his interesting talk. Thank you very much.
Thank you.
And the next talk will be by Matej Ciocarli. Matej is Associate Professor of Mechanical Engineering at Columbia University. And his work is on robot motor control, mechanism and sensor design, planning and learning. And the goal is to demonstrate complex motor skills, especially dexterous manipulation for robotics. And in recognition of his work, Matej has been awarded the Early Career Award by the IEEE Robotics and Automation Society, and also a Young Investigator Award by the Office of Naval Research, among the others. And the title of his talk is How to Make Sense and Make Sense of Contact in Robotic Manipulation. So thanks, Matej, for joining these sessions, and please, the stage is yours.
All right, thank you so much. First of all, can you see my slides and hear my voice?
Yeah.
Yeah. Excellent. So it's a great honor to be invited to jam with such distinguished musicians and in front of such a distinguished audience. So thank you so much. The only thing that would be better would be to be that in person with you, but unfortunately, that's not the world we are in right now. So our lab focuses primarily on robotic manipulation, and we are finding out pretty much every single day how that really implies studying the physical hardware, the mechanical aspects of the hand, but also the sensorial and the computational aspects of the task. It's not a kinematics and actuation or sensing or a modeling or control problem. It's really all of these. And in my talk, I'm going to cover a range of projects touching on just about all of these aspects of manipulation. And it's what makes it a very difficult skill, but also a very compelling one to work in. So I'm going to start more on the kinematics and actuation side of things, more on the physical hardware side of things, if you wish, with a project that's motivated by a very, very clear use case. And that is NASA's Astro B robot. You can see the Astro B in these images on the space station. The American astronaut Christina Koch on the left and David St. Jacques, the Canadian astronaut on the right, they are both interacting with the Astro B. You get a sense of the size of the thing. It's a cube about 30 centimeters in each dimension. There are 3 of them right now on the space station, intended as monitoring devices, sensing platforms floating around the space station. And even though their main role initially was as sensing platforms, NASA has always been interested in adding manipulation capabilities to the Astro B. And the first thing that they were looking for was the ability to just perch, grab onto handrails, of which there are many on the space station. And about 5 years ago, our lab designed a perching gripper. The perching gripper you can see in that image right now. We designed it. Yes.
Sorry for interrupting you. There is a gray rectangle in the bottom right corner of your slide. Yeah, there.
That is where I have the window for Teams. Is it gone now?
Perfect.
Okay, thank you. Okay, so we designed that perching gripper about 5 years ago for grabbing onto handrails, and right now there's one of those grippers in orbit waiting to be commissioned, and we are very anxiously waiting to see how it actually works in orbit. But that was always going to be just the start. We've always been interested to see if we can endow the Astro Bee with actual versatile manipulation capabilities. Can it genuinely be useful in orbit in terms of, for example, delivering objects to astronauts and interacting with a wider range of objects and the wider range of shapes? And it immediately became clear when we looked at the list of objects that we'd like the Astro Bee to manipulate, it immediately became clear that just a simple 2-finger gripper is unlikely to be versatile enough to do robust manipulation of such a wide range of shapes. So we started looking at more complex kinematics. And based on our own intuition and know-how, we eventually decided on a kinematic configuration with 3 fingers and 8 joints in total. We felt that that would give us the versatility that we need. And as I'm sure many of you who work in manipulation are very, very well aware of, a hand with 8 joints has an 8-dimensional posture space. So any hand configuration is a point in this 8-dimensional, very high-dimensional posture space. Here is my best attempt to put an 8-dimensional posture space on a 2-dimensional slide. So however you shape the fingers, any finger configuration corresponds to 1 point in this 8-dimensional posture space, where 1 dimension corresponds to each degree of freedom. And once we have a set of grasps that we'd like this hand to be able to execute, this gives us a cloud of points in this 8-dimensional space. And we'd like the hand to be able to execute all of these grasps in stable fashion. But now to get to the essence of the problem is that there's just no way we're going to put a hand with 8 motors inside the Astro Bee. The payload bay of the Astro Bee is maybe 15 by 15 centimeters, something like that. You are just not going to package a hand with 8 motors inside that tiny space. So the only way this is going to work is if we have a heavily underactuated hand, a hand with many fewer motors than degrees of freedom. Maybe 1 motor, maybe 2 motors is the best we can hope to package in such a tiny payload bay. And again, as I'm sure many of you know, once you have underactuation, if you have fewer motors than degrees of freedom, underactuation introduces a manifold in this high-dimensional posture space. If each joint is independently actuated, then the hand can happily shape itself to go anywhere in this posture space. If it's underactuated, the hand will only have access to some lower dimensional manifold that's embedded in this high dimensional space. So then the problem becomes, okay, we have a hand, we'd like it to execute all of these grasps, so we'd like it to be able to reach all of these points in the posture space, but underactuation introduces a manifold, and that's the only subspace that the hand can travel along. How do we make these two work together? Obviously, we have to shape the manifold introduced by underactuation in order to hit the grasps that we'd like to be able to execute. And because this manifold is introduced by underactuation, we refer to it as a mechanically realizable manifold, as opposed to, for example, the idea of synergies that's very, very well established, which refers to software manifolds introduced computationally. This is a mechanically realizable manifold introduced by underactuation. So how do you shape the manifold introduced by underactuation in order to hit very, very specific grasps that you'd like to execute? And in particular, if you look at exactly what's the mechanism by which this underactuation manifold gets created, there are a number of parameters pertaining to the underactuated transmission that you can tune. That's what you're actually controlling. So if you look at this schematic, we have a 3-fingered kinematics, and we have here a single actuator. We are assuming a single motor, and the motor is connected via tendons, and the tendons are denoted by the red lines. That one motor is connected via 3 tendons to all the 8 joints. And what happens is that we can control transmission parameters such as the radii of the pulleys that the tendons go over, or the stiffnesses and the preloads of the springs that provide the extension forces. The motor only flexes the fingers. All extension is passive, provided by springs. So all of these parameters, tendon routes, pulley radii, spring stiffnesses, spring preloads, these are the design parameters that end up determining how the manifold of underactuation looks like in the high dimensional posture space. So can we find the values for these design parameters that give us the desired manifold in the high dimensional posture space? And the algorithm that we introduced, we showed that yes, this is possible. And we introduced a new algorithm to do this, given a kinematic configuration and given a set of grasps that you would like to execute. Our design optimization algorithm combines exhaustive search in the outer loop. It's an exhaustive search over design parameters. It uses convex optimization in the inner loop, which is very important because if you have an exhaustive search outer loop, the inner loop needs to be computationally very efficient. So we use convex optimization in the inner loop that looks at the stability of each grasp. But when we put it all together, this design optimization algorithm is able to find the optimal values for all of these parameters that give you the right shape of the manifold. This is what this looks like in practice. This is the very, very first prototype that we built, which we had before it even had a motor, just to illustrate that, look, the real power is just in the kinematics. Let me play this again from the beginning. You can see that as the hand is being actuated, the hand just cycles through a set of grasps. The fingers come together for a pinch, and then they sort of get out of each other's way so that you can do a power grasp, an enveloping grasp. And this is all with a single actuator. And all of this movement is physically induced just by the transmission, the underactuated transmission. And it's not just that the hand can shape the fingers to mime all of these grasps. Our optimization algorithm explicitly assures that the grasps are quasi-statically stable as well, so that you can go ahead and grasp. And this is the range of objects we're looking at. This is the next version of the hand where we actually went ahead and we put a motor on it. And you can see how it goes through a power spherical grasp, goes to a pinch, then fingers get out of each other's way to do an enveloping grasp. And even with a motor, you can have this stability guarantee for all of these grasps. And the other thing that we found interesting about this tool is that since it's an optimization algorithm that explicitly optimizes a metric, there's an optimization objective that you're looking to optimize, then you can also use it to quantitatively compare different designs and see which of these designs gives me what value of the objective that I'm optimizing. So for example, we were able to quantitatively compare a design with a single motor versus a design with 2 motors, where the second motor affects the roll degree of freedom at every finger, versus another design with 2 motors, where both motors are connected to all the joints, so just different kinematics. So you can think in a way of the outcome of the optimization algorithm that we run as a hand quality metric, a quantitative hand quality metric that is something that I feel could be very useful in the field as we go forward for comparing different designs. And for us, for this use case, for example, the result of this very quantitative comparison between different kinematics was that, no, really, a single motor is the sweet spot in terms of bang for the buck, if you wish, ability versus cost and complexity. So that's the one we ended up going with and integrating with the Astrobe. So this is last November, a version of our hand at NASA Ames on the Astrobi ground unit on a granite table in simulated microgravity, demonstrating the integration with the Astrobi and the ability to do all of these grasps. This is the version that we decided to go with. And since then, we've also redesigned it to fit in the payload bay. So now it does fit in the payload bay of the Astrobi. So we are anxiously hoping to be able in the next couple of years to go through the flight certification process with this, because as you can imagine, NASA won't send to orbit things that can spontaneously catch fire inside the space station. So this has to be flight certified, and we're hoping that there's a chance that in the coming years we'll be able to send this to orbit. That's from an applied perspective. From a theoretical perspective, what this hand does is what our method does. It is the first design optimization method that can fit an underactuation manifold to desired grasps while guaranteeing that that manifold is achievable by a physical transmission, which is why we call it the mechanically realizable manifold. So we were pretty excited about these results and the hand that it produced, but there were still some things about the approach that didn't quite sit that well with us. And in particular, yes, we can optimize the hardware, but the fact that the target grasps, the one that you're optimizing for, are still selected by a person, that didn't quite sit well with us because that seems to be this disconnect. So first of all, we prefer to avoid this manual input, having a person have to tell you exactly what are the grasps that you want the hand to achieve. Plus, a person doing that doesn't really understand necessarily underactuation. Maybe they will choose grasps that are just not well suited to be realized in an underactuated fashion. If you knew that you were choosing grasps specifically for an underactuated physical mechanism, maybe you would choose them differently. So we'd really like to combine the process of optimizing the hardware with the process of selecting the grasps that the hand would have to execute. And of course, finding grasps of objects is a topic with a long and distinguished background of literature, the field of grasp planning, but this is the year 2020. So what do we like to do these days as opposed to the kind of a self-contained topic of grasp planning? We really like to think of things as policies. So something that chooses a grasp is a policy, a software grasping policy. And in the last couple of years, we've had kind of a revolution in the field in terms of finding policies for a wide range of tasks. We've seen that the field of model-free reinforcement learning, and specifically deep reinforcement learning, is really, really good at finding policies. So let me quickly walk you. I'm sure many of you do know the fundamentals of deep reinforcement learning, but just to have a common frame of reference, let me quickly lay down the sort of the basics here. So how does this idea of policy optimization work? You have a computational policy that is oftentimes represented as a deep neural network, a multi-layer perceptron in many cases, which takes in observations of the world and it produces actions. So the computational policy tells you which actions to apply. Usually the actions come in the form of motor commands. The motor commands then get applied to the hardware. The hardware does something in response, which causes the world to evolve to its next state, and the cycle recommences. And the whole point of policy optimization, simplifying it to the maximum, is to find the parameters of the policy, shown in blue in my slide, which means the weights and the biases of the neural network in most cases, such that the actions that the policy spits out are appropriate for the observations and the state that you're in. So policy optimization just says, find me the policy parameters that give me the best actions in the most meaningful states. So this is how policy optimization works at a high level. What the field quickly found out in the last couple of years is that this needs way too many training samples to do on a real robot. You cannot train this policy, you cannot optimize those parameters on a real robot. It just takes way too many training samples. So instead, we found out as a field that there's so much we can do if we do this optimization loop on top of a simulator. And then the real robot, the hardware, is simulated by a general purpose simulator treated as a black box for all practical purposes, usually MoCA or PyBullet or a couple of other options. So now everything stays the same, except that all the hardware is inside a simulator. Well, if the hardware is inside the simulator, then we can also optimize hardware parameters, right? Not just the parameters of the policy, but design parameters of the hardware, because inside the simulator, we can change anything about the hardware at any time. So maybe we can do an outer loop, not shown here, where we also optimize hardware parameters. But that still wasn't what we were looking to do. We wanted a much more intimate connection between the software optimization and the hardware optimization. So what we did, and this is very, very active work that we are just writing for publication right now, we said, what if we take part of the hardware, and specifically the part of the hardware that we'd like to optimize, and also express it as a computational graph. So we take it outside of the general purpose simulator, and we simulate part of the hardware ourselves, modeled as a computational graph. And in our case, for example, the part of the hardware that we're looking to optimize is the transmission. And if you think about it, what does a transmission really do? A transmission takes in motor commands and converts them to joint torques. So the input is motor commands, the output is joint torques. It really is just a policy. Conceptually, it's no different than the computational policy. The key here is, are you able to model that physical piece of hardware as a computational graph so that it can be differentiable? And we show that for some specific cases, like, for example, the transmission in an underactuated hand, yes, that is indeed possible. We can model that transmission as a computational graph with structure dictated by the physics laws, by Newton's law, Hooke's law. So this is not an arbitrary multilayer perceptron. The computational graph has to have a very specific structure because it implements the laws of physics, but it is indeed possible. And then the parameters of the hardware, things like tendon routes, pulley radii, spring stiffnesses, spring preloads, they are the parameters of the hardware policy, and they are perfectly equivalent to the parameters of the software policy, maybe the weights and the biases of the neural network. So all those things shown in blue on these slides are conceptually equivalent to each other. And because both the computational policy and the hardware policy are expressed as autodifferentiable computational graphs, now we can have a gradient flowing through both the green box and the yellow box here, and we can run policy optimization jointly on both the computational policy and the hardware policy. And we refer to this approach as hardware as policy. And the actual algorithm that you use to do policy optimization could be anything. We are agnostic to that. You can use TRPO, PPO, SAC, DDPG, whatever your favorite algorithm is. So we're looking at this right now with the same problem that I talked about earlier, which is optimizing this three-fingered underactuated hand. In MoCA, this is what it looks like with unoptimized hardware parameters. It's very unstable. It fails to grasp just about anything. And this is after we've run our hardware as policy approach. The inner algorithm is TRPO, but we could use other things as well. And it optimizes both the computational aspects and the mechanical aspects to do stable grasping. And it does it way more efficiently than using an outer loop for optimization of the hardware or other state-of-the-art gradient-free optimizers like CMAES. And we are right now in the process of physically building the hand that our optimization says should work, and we're fairly confident that the physical prototype will confirm these results, and hoping to submit that, for example, to Coral in a couple of weeks. But what's really exciting to us about this approach is that we're really thinking about, where does intelligence reside? And for a long time, we've said, yes, intelligence can reside in software with the right sensor input, but really intelligence can also be embodied in the mechanism design. And this isn't a discrete choice. We think that the most powerful solutions will be somewhere in the middle, where you combine mechanical intelligence with computational intelligence, and especially if these two are designed for each other and optimized for each other so that they can leverage each other's strengths and complement for each other's weaknesses. And this is why we feel that joint optimization in the same inner loop with a gradient flowing through both of them is a very, very powerful paradigm going forward. The next piece of the puzzle, if you wish, especially if you talk about computational intelligence, is sensing. And there really cannot be meaningful computational intelligence without the appropriate sensing going in. And we've invested a lot of resources in our lab over the last 5 years on tactile sensors, building better tactile sensors, feeling that what we have out there is really not what we need for building into robot hands. And in particular, none of the sensors that were available when we started this work were able to give us the kind of rich data we wanted, but very importantly, with good coverage of curved surfaces. We did not want sharp edges or corners in our fingers that were not covered by sensors, because that's exactly where you're going to make contact if you have a sharp edge or a corner on your finger. And if you don't have contact sensing there, then you are blind to all of that information. And we needed sensors that would be easy to integrate in a robot hand. So not, 1,000 wires coming out of it so that you can show it on a workbench, but never inside a robot hand. Wiring is the death of the roboticist. I think sooner or later, any robotics project, as we all find out the hard way, comes down to, can you wire the thing when you put it together? So let me briefly walk you through the high-level concept of how we are doing tactile sensing. We refer to this as overlapping signals. So if you imagine a tactile sensor, which is this gray slab here, with two embedded terminals in it, and I'm going to keep it fairly vague for now, and we can measure some signal between these two terminals, and that signal is affected by touch. So if the sensor is contacted, for example, as denoted by the red circle, then that signal between our terminals changes. And maybe it's resistance, maybe it's capacitance, could be many, many things. And now imagine that instead of two terminals, we have n terminals embedded in our sensor. What that means is that we have n squared of those signals if we measure the signal between every pair of terminals, and all of those are affected by touch in some way. So the number of signals is quadratic in the number of terminals. That's the great advantage of this idea of overlapping signals. It gives you a very, very rich data set with very few wires, which is what we were hoping for. So we implemented this general concept. First, we went with piezoresistive materials, but we quickly went away from that because of difficulty in manufacturing and hysteresis. And then we tried light. So half of our terminals are LEDs and the other half are photodiodes. So we measure how light transport is affected by touch, and light is just is wonderful. There's very little hysteresis. It's fast, it's easy to manufacture. And we were hooked. We never went back to electricity. So first we built a 2D version of our sensor, but that was really just a stepping stone towards the 3D version, which I'm showing a cross section of here. It's a cylindrical finger with a hemispherical tip with LEDs and photodiodes embedded in a transparent layer, and the transparent layer is about 7 millimeters thick. And then there's a reflective layer on the way on the outside to keep outside light from going in and to keep inside light from coming out. This is what the whole thing looks like as we build it. So it starts off with a 3D printed skeleton. On top of that, we have a flexible circuit board with 30 LEDs and 30 photodiodes. Then on top of that, we have our 7mm thick transparent layer, which you can see in the middle image. And then on top of everything, we have the reflective coating. So we have a total of 30-something LEDs, 30-something photodiodes, so about 1,000 signals if we look at every pair of LED and photodiode, and a single cable with 14 wires coming out of the finger, so very easy to wire up. The sort of the catch of this nature of sensor is that the data is very, very rich, but very hard to make sense of analytically. So this is a sensor designed from the beginning for machine learning. And one way you can do this, for example, this is how we collect labeled training data for our tactile fingers. You can see one of our fingers mounted on a frame, and then we have a robot with a linear probe and the load cell that's poking the finger. And here we are collecting labeled training data with very precise location and force information so that we can train our favorite supervised classifier or regressor to then be able from the raw tactile signals to predict location and force. Let me start this video as well. And this is what that looks like in practice. So once we've trained our regressor, then we are able to do very accurate touch localization, touch force. And we have a hemisphere that's fully sensorized. We have a cylindrical body that is sensorized for more than half its circumference. So there are no sharp corners, sharp edges where you would make unsensed contact. So we think that this is really well suited for manipulation in clutter. We have in the paper, we have all the quantitative evaluation that I'm not going to bore you with right now, but this is what we're going towards, which is dexterous hands. We've built 2 dexterous hands in our lab equipped with these sensors. One of them also has proprioception, so torque sensing at every joint. The other one does not. And we are very, very actively every day working on manipulation algorithms that make use of these sensors, both model-based and model-free, just end-to-end sensory motor learning, and hoping to have more to report on this in the coming months or years, something that we're very excited by. And then I would like to take just 5 more minutes to talk about modeling, which is sort of a more abstract theoretical part of our work. But we still feel that even in this world of model-free reinforcement learning, there's still a very important place for model-based control and understanding of what's going on. Plus, this is work that builds on very, very solid foundations that were laid by people like Antonio and Matt Mason and Domenico Praticizzo and Jeff Trinkle, Ken Salisbury. So I couldn't miss the opportunity to at least briefly talk about what we're doing in terms of modeling. We are looking at frictional contact modeling, which is important for manipulation, but also for locomotion, as you would expect. And I'm sure many of you know, but maybe to other folks it'll come as a surprise, that really friction modeling is not a fully understood, fully solved problem. And you might be tempted to say, wait, what? Coulomb friction is not well, we don't have mastery of Coulomb friction in our models. And it turns out that we don't, especially when it comes to a part of Coulomb friction that's rarely considered, which is the maximum dissipation principle. So I'm sure everybody knows that the Coulomb friction model states that the friction force has to be less than the normal force times some friction coefficient as long as the contact is sticking. However, so when a contact is sticking, friction can be anywhere inside the friction circle, which is the view of the friction cone from the top. But the Coulomb friction model also states that when the contact is slipping, friction must be as large as possible and must perfectly oppose the direction of slip. In other terms, when a contact is slipping, friction must dissipate as much energy as possible, which is why this is referred to as the maximum dissipation principle. And the maximum dissipation principle is incredibly difficult to model because it's C1 discontinuous and non-convex. So no existing solvers, three-dimensional solvers for contact stability, quasi-static quantic stability, can take into account the maximum dissipation principle in a computationally efficient fashion. So what we did, we looked at this problem for three-dimensional grasps, and we realized that you can approximate the maximum dissipation principle as a mixed integer program where you discretize the friction circle, and you can constrain friction and slip. They should be right on top of each other. That's what the Coulomb friction model says. We cannot constrain them to be right on top of each other. We can at least constrain them to be in the same quadrant of the discretized friction circle. And then once we find out what quadrant they are in, we go ahead and we adaptively refine the discretization, but just of the quadrant that's relevant. And eventually we can constrain these tighter and tighter and tighter, and we were able to prove that this is formally a tightening approach to arbitrary accuracy. And because we're solving a mixed integer program at every step of the way, this is still computationally efficient. So it is formally a tightening approach, and it does allow us to include the maximum dissipation principle with arbitrary accuracy and in computationally efficient fashion. And you know, why do we care about that? We care about that because this is the only way, we think, in which you can take into account passive effects. So if you think about the batted hand, many of you know the batted hand, it has these very highly geared servo motors that are not backdrivable. So you can push against a joint and it will just passively resist that because the motors are not backdrivable. So some disturbances the grasp can resist just by virtue of the hand, the joints not backdriving. Other disturbances you cannot resist passively. You need active force generation, like squeezing the object in order to resist them. And without taking into account energetic considerations, we don't think it's possible to distinguish between those effects. But with our approach to contact modeling, we just show that it is possible to distinguish between active resistance and passive resistance for a wide range of tasks. So those are the projects that I wanted to go into in a little bit more detail. Some things that unfortunately I don't really have time to do anything other than show the eye candy videos. We are very actively working on teleoperation, especially with novice teleoperators for hands that are not anthropomorphic in nature. Things like pick and place, more complex tasks like valve assembly, valve disassembly. And even looking at things like forearm electromyography as an input device for such teleoperation tasks. And then a project that I wish I would have had more time to talk about, but unfortunately it's not the case, is an exoskeleton, a soft exoskeleton for stroke patients, where we're looking at intent detection, we're looking at mechanical design. So But ultimately, it is about asking ourselves, really, where does intelligence reside in this very, very complex system that is the human manipulator? So if nothing else, then I hope that I've just convinced you that it's really important that we look at the mechanical aspect, the sensing aspect, and then the computational aspects all together. And hopefully that's what our next advances will be. Thank you.
Thank you very much, Matej, for the nice presentation, which has covered different aspects in your work. I have one quick question on a curiosity related to your work, especially for what concerns the part on tactile sensing, if I can. So basically, with your sensors, you can retrieve the normal force and the contact point on the fingertip. And I think it's well in line with also the intrinsic tactile sensing approach, which was developed in the past and now adapted to softer surfaces. But my question is that there are also other types of tactile sensors used for grasping and manipulation. Based on your expertise, this is a very challenging question. Which information, of course, force and contact point are crucial for grasping and manipulation, but which additional tactile information do you think could be extremely important for manipulation purposes, and how to retrieve and handle this information, for example, through machine learning?
That's a very good question. Obviously, shear would be a fantastic additional component to have. And our sensor, we don't think it's particularly well suited for giving us shear forces or shear moments. We're hoping that at least in the hand that has torque sensing at every joint, we'll be able to compensate for not having shear forces based on joint torque sensing, if we also know contact location. There are other sensors right now. There's a line of work from Ted Adelson's gel site sensor, and then Gel Slim that Ted and Alberto Rodriguez built, work from Berkeley on the OmniTact, that are putting actual CCD or CMOS cameras inside the finger, which also has the potential to gives you even richer data, and they can also tell you something about shear forces. So that's also a possibility. And of course, those are also sensors that are built exclusively for machine learning, and there's nothing else that will work on such rich data. So I think shear is big. Then there's vibration and slip. We're hoping that at least for manipulation where you can be in a quasi-static regime most of the time, we're hoping not to run into things like slip and vibration. But maybe as a next step, we've thought about putting microphones or IMUs, accelerometers, in our sensor so that we get some information about slip and vibration. So I would say shear first, slip and vibration next, and then we can also talk about temperature or microtextures or other material properties.
Yeah, thank you very much. I completely agree also with your point, which makes perfectly sense. So I think we are a little bit late. So I think we should move to the final talk of today. But I would like to thank Matej for the very interesting and inspiring talk, which has covered many important aspects for our community. So thank you very much, Matej. And it was really a pleasure for us. Now let's move to the final talk. So the final talk will be a joint presentation by Dr. Mark Spong and Dr. Alireza Mohammadi. And Dr. Spong is Professor of Systems Engineering and holds the Excellence in Education Chair at the University of Texas at Dallas. He is past president of the IEEE Control Systems Society and has made fundamental contributions in robust and nonlinear control of robot manipulators, teleoperators, and also other aspects in robotics. And his notable awards include the Rufus Oldenberger Medal and the Bode Lecture Prize, and also the Pioneer in Robotics Award, among the others. And Dr. Alireza Mohammadi is an assistant professor in the Department of Electrical and Computer Engineering at the University of Michigan, Dearborn. And he leads the Robotic Motion Intelligence Lab, and his research interests include robotics, of course, and nonlinear control systems, but also autonomous vehicles and mechatronics. So the title of the talk is Integral Line of Sight Path Moving Control of Magnetic Helical Microswimmer Subject to Step Out Frequency. And thank again to Dr. Mohammadi and Dr. Spong, and the stage is yours.
Okay. I don't see my, there we go, I'm on. Good morning from Dallas. I know it's evening for most of you, so we're between you and dinner now. I'm just going to make a couple of remarks and turn it over to Alireza for the rest to try to set the context here. As you can see, we're talking about helical micro robots, and the work that Alireza will present includes some new planning and control results. One of the main motivations for this work was dealing with input saturation. Of course, all systems are subject to input saturation. This has not been considered much on this particular problem. Particularly here, we're talking about saturation with respect to what's called the step-out frequency, which limits the rotational motion of the microswimmers and their velocity. Interestingly enough, this idea that we use essentially reduces this to a quadratic optimization problem. And historically, this goes back to actually the very first work I did in robotics in the early 80s, where the first problem I considered was the actuator saturation in manipulator control. And we use quadratic programming, a pointwise optimization to deal with actuator saturation. That, after many years, this idea is sort of making a resurgence in work of people like Jesse Grizzle and Aaron Ames in biped locomotion, where they consider actuator saturation and reduce it also to a pointwise quadratic optimization problem. So this idea is sort of coming full circle now, which is nice to see, kind of an old idea, seeing new applications. And the new application here, of course, is to use quadratic programming to deal with this saturation issue in these helical micro swimmers. So that's really all I wanted to say before turning it over to Alireza. So thank you all for again for the invitation, and I will see many of you tomorrow as well. So Alireza, it's all yours.
Thank you very much, Mark. So do everyone see my screen right now? And do you see my screen right now, or?
I can see it.
Okay, fantastic. Yeah. And do you hear me clearly as well?
Yeah, thank you.
Oh, fantastic, fantastic. So thank you very much, Mark, and thank you very much to the organizers of the Robotics Jam session at the University of Pisa. So there are two very interesting coincidences regarding this talk. The first one is that much of the modeling framework is based on the prior research of Jake Abbott. So it's a very interesting coincidence, his research on magnetic microrobots. The second coincidence, it's related to the University of Pisa, and I will talk about it in the very last slide. Okay, so let's, get started. So in this presentation, we would basically investigate this problem of straight line path following for a specific class of helical microrobots. The current results that I'm going to present are in a basically draft submitted to Automatica. It's currently under review. In order to first see how these magnetic microrobots work, let me show you a very brief video of just an idea of their locomotion mechanism. So as you can see, they move like screws. They rotate in their fluidic environment, and the actuation method is using basically external magnetic fields. And these microrobots have got many applications in viscous fluidic environments. For instance, they can be used for targeted drug delivery, or they can be used for cell manipulation and characterization. There are two main actuation technologies for these microrobots. One is basically more futuristic. It's based on the concept of molecular motors, and some sort of protein with a specific structure would be used to induce a desired motion. But of course, our technology right now is very primitive, and we do not have, we cannot efficiently realize these molecular motors yet. But the other way of actuation technology, which is more accessible to us right now, is the untethered magnetic actuation, and basically using magnetic coils and external magnetic fields, we would basically induce desired motions in these magnetic microrobots. The good thing is that they scale very well, both in terms of the microfabrication of the microrobots and also wireless power transmission and control. Okay, so basically these swimming microrobots come in different morphologies. One very primitive morphology is a bead-like one. It's basically just you have got a spherical bead or a spherical, basically a magnetic cylinder or a magnetic sphere, and then using a gradient pulling, you would induce the desired motion in your robot. The other two, which are the flexible tail morphology and helical morphology, are bio-inspired. So for instance, we saw a video from the helical swimming. Let's also see a video from the flexible tail swimming. And this is in Metin City's lab. Basically, it's like more like a snake locomotion, but of course in a fluidic environment. And you can see that as the microrobot wiggles its tail, it would propel forward in its environment. And of course, we have got the helical microswimmers, where by rotating an external magnetic field around the helical microrobot, you would induce a screw-like forward motion in your microrobot. Now, the interesting thing is that there is always a specific size below which using helical propellers and elastic tails is more efficient than pulling microbeads. So that's why most people use basically either structures with flexible tails or helical structures. Now, you might ask yourself then, why specifically helical as opposed to, using the flexible tail structure? One of the reasons is that, first of all, the direction reversal is very easy. Just by changing the direction of the basically rotation of the magnetic field, you can induce motions in different directions. The other one is that because there's no wiggling tail motion, we can have a smooth transition from lumen, basically meaning that inside the tubes and narrow structures, to open environments. And of course, we can also use non-uniform magnetic fields. Okay, so as Mark mentioned, we basically for solving our control problem, and I will present a detailed formulation of the control problem in a few minutes. But let me give you a very quick background on the control ideas that we are borrowing to solve this interesting problem. The first one is coming from the underactuated marine craft control, and it's the idea of line of sight path following. It basically gives us a guidance law for putting the microrobot in a proper direction. And it's basically inspired by the line of research by Christine Peterson. And of course, the dynamic model, as I mentioned in the beginning, is completely based on the derivations of Jake Abbott, or one of the presenters in the Robotics Jam session. And of course, just as Mark mentioned, one of the fundamental components of our solution is based on quadratic programming. And as we go on, we will see how it would be used. But as Mark mentioned, basically this quadratic optimization was one of the first few lines of research by Mark for basically controlling of industrial manipulators with bounded inputs. And he got his idea actually from the optimal aiming strategies from the power systems literature, and specifically the work of Barnard back in the 70s. Okay, so let's see how we can basically dynamically model a helical microswimmer. So as I mentioned, the primary form of locomotion in the magnetic microswimmers is based on a rotating magnetic field that would basically induce a propulsion in the microrobot in the forward direction. Now, the robot geometry is determined completely by the number of turns of the helix pitch angle, and the helix radius RH, and of course there is a magnetic head which has got radius Rn. Having the geometry of our robot, let's also fix a coordinate system to basically our robot. So first of all, we have got the helix coordinate frame, XH and ZH, which are attached to the helix center. And we have also got a global coordinate frame because we would like to be able to control the micro robot and make it to converge to a proper path. We need to define this global coordinate frame. And basically, its coordinate axes are given by E hat X and E hat Z. And E hat Z is basically parallel to the gravity that is acting on the swimming micro robot. Now we also let the position of the center of mass of the micro robot be given by the vector P and its velocity given by V. Now we make true a specific modeling hypothesis, but I should mention that, or as we will see later, our control would formally guarantee that these hypotheses are satisfied in action. Let me state these hypotheses, and then I will tell you why actually these hypotheses are useful. The first one is that, first of all, the microswimmer needs to rotate in synchrony with the external magnetic field, which is actuating the microrobot. And the second one is that the central axis of the microswimmer, XH, is always aligned with the field axis. Now, using these two hypotheses, actually we can prevent some technological barriers in controlling these microrobots, because if the central axis of the microswimmer is aligned with the field axis, then we do not need to sense the orientation of the microrobot. You can imagine that because these are very tiny, sensing their orientation would be really challenging. Yes, it's easy maybe to find the position of them in basically using a camera, but sensing the orientation or estimating the orientation is a challenge. The second thing is also that under H1 and H2, if we somehow satisfy the modeling hypothesis H1 and H2, then the motion of the microswimmer would be constrained to a plane as opposed to a 3D motion. So specifically, if these two are satisfied, the motion of basically the microrobot would be constrained to the plane given by the directions G and the central axis of the microswimmer. Okay, so under these two hypotheses, Jake actually derived the dynamic model of the microswimmer in the plane, and it's given using this first order differential equation. P dot, or the speed of velocity, is equal to a constant which depends on the physical parameters of the microrobot, U, which is the microswimmer angular velocity, and it can be directly commanded using the intensity of the outside magnetic field, and d mu, which is a disturbance vector, and it lumps the effect of weight and other disturbances like blood flow or fluidic pressures. The thing is that in our control implementation, we do not necessarily need to know the exact values of E11, this constant parameter, and the disturbance vector. We will see how we can basically, how our control is capable of addressing these two unknowns, E11 and d mu. Okay. Now, the concept of a step-out frequency. Basically, as Mark mentioned, there's a major control limitation for basically actuation of magnetic microswimmers, and it is because of the existence of an upper limit on the rotational frequency of the robot body about its axis. And basically the idea is that if the magnetic field starts to rotate faster than a certain frequency, the speed of the micro robot would decrease in a very, in a sense, it would start decreasing. Also, it would perturb our assumptions of H1 and H2, meaning that there would be certain limitations on the way that we can control. So our desire is that we do not want to go above this step-out frequency. So our control, as we will see, will ensure that we would not violate this step-out frequency constraint. Okay. Now, let me also give you a background on some experimental observations that actually Abbott and Nelson, Jake and Brad Nelson did in their experiments, is that, first of all, as long as our micro robot is commanded a smooth velocity profile with limits on acceleration, then H1 and H2, meaning that rotating below the step-out frequency, or actually rotating in synchrony with the external magnetic field, and alignment of the field rotation axis with the micro-robot axis would be met. Now, one of the beauties of our solution is that we will see H1 and H2 would be satisfied. As I said, our control scheme formally guarantees that or commanded a smooth velocity profile, or commanded velocity profile is smooth, and a step-out frequency constraint is met. Okay, now let's, having this background, let me formulate the control problem, and then we will proceed forward with the solution. So first of all, as I said, we would like the robot to converge to a desired straight line. So let's assume that the desired direction of the line is given by this vector E hat theta r. And E hat theta r determines basically the straight line path that goes through the origin. Of course, we can easily translate the origin. So the problem is, in a sense, the origin invariant. So we assume that our line is passing through the origin. And of course, we are given the step-out frequency constraint, omega SO, and some unknown disturbance input, d mu. We assume that the d mu is piecewise continuous and bounded in magnitude. And we would like to choose a control input so that the micro robot would converge to a line P while the step-out frequency constraint is satisfied for all time. So this is our control problem formulation. So the solution to this control problem formulation comes in two steps. In the first step, I assume that there is no step-out frequency constraint, and I find the proper guidance law for my micro robot. After finding the proper guidance law and studying its properties, I would basically bring in the step-out frequency constraint, and I will show how quadratic optimization is useful for addressing that step-out frequency. So, as I said, the first step is how we should basically command the velocity of the micro robot so that it would converge to the desired path P. Actually, looking into the literature, there's a very interesting, line of research, specifically by the NTNU, Norwegian University of Science and Technology, and they have basically developed a line of sight, basically guidance law. And the idea is that you always point your vessel or marine, or in our case, the micro robot, such that it points to a distance equal to delta LOS ahead of its current location. Now, there's also a dynamic parameter in our basically guidance law, S, that would take care of the unknown disturbances. So basically, or as you can see from these two equations, we have got a VDPS, which is the desired guidance law. It comes from the line of sight, from the underactuated marine craft control. And it also depends on a dynamic variable. And that dynamic variable actually takes care of the unknown disturbances that are acting on the micro robot. For instance, it can be the unknown constant E11 or the unknown gravity vector acting on the microrobot. Okay, so this guidance law is here. Now, in order to study basically the behavior of the microrobot under this guidance law, let's do some simple geometric coordinate transformation. Basically, I define two variables, epsilon and z. Epsilon is basically the perpendicular distance of the microrobot to the line P, and z basically determines the position of the microrobot on the line, meaning that if the microrobot has converged to the line, the z coordinate can be used to describe where the microrobot is located on the line. In a similar fashion, I can also break in the disturbance vector into two components. One, a component perpendicular to the line, and the other, a component parallel to the line. Okay. Now, with these geometric transformations, I can basically state the performance of the closed-loop control system under the ILOS guidance law. Still, we are not dealing with the step-out frequency. We will bring it in the next slides. But using some standard Lyapunov arguments, we can show that if the perpendicular disturbance, meaning that the component of disturbance that is perpendicular to the line is equal to 0, then epsilon and the dynamic variable s would converge exponentially to 0, and the convergence is globally exponential. Furthermore, if the basically parallel component of the disturbance to the line is equal to 0, then the velocity of the microrobot would also converge to this value, which is given by E11, which is depends on the physical parameters of the fluid and the microrobot. Alpha D, which is a control parameter, it comes from the guidance law. Delta LOS, again, it's the look-ahead distance from the guidance law, and E hat theta R is, of course, the direction of the line. Now, what would happen if we have got perpendicular components of the disturbance? Well, it is possible that if we, or actually mathematical derivation gives us guidance on how to choose the parameters KD, alpha D, and delta LOS, such that even in the presence of disturbances, we would converge to basically a distance arbitrarily small to the line, meaning that though we do not have exact convergence, but the distance between the microrobot and the line can be made as small as possible, provided that the control parameters are chosen properly. In our paper, we also give conditions on how to choose these basically gains. Okay, so for now, we have determined the guidance law. Now let's bring in our step-out frequency constraint. So in order to address the issue of this upper bound on the norm of the control input, we use the optimal decision strategy, which was investigated by Mark back in the 80s. And let me explain it in the following way. So suppose that our control system is given by this nonlinear control affine form, and it's exactly the same as the control form that we have got for our swimming microrobot. We would like to make sure that our control input always satisfies a certain inequality given by this basically inequality on the magnitude of the control input for all times. Of course, for the case of the microrobot problem, Umax, or the maximum input possible, is the step-out frequency. Now, given our desired vector, VD, so in the case of the microrobot, the VD comes from the ship or the marine guidance law, we would like to find the feasible direction V such that V is as close as possible to VD, while basically the constraint of the magnitude of u less than or equal to u max is satisfied for all time. So the geometric picture is shown here. Basically, the thing that this quadratic optimization or the optimal decision strategy does is that it would find the best possible velocity of the basically vector field, p dot star, such that it satisfies the constraints, and at the same time, it's as close as possible to the desired basically guidance law. Okay, so this is the idea of the optimal decision strategy. Now, in the case of our magnetic micro-robot problem, we have got the reference vector field, which comes from the ILOS-based guidance law, and our quadratic optimization reduces to this quadratic optimization. Now, as you can see, there are some expressions. A mu, it is dependent on that physical parameter E11, which depends on the physics of the microswimmer and the fluidic environment. It depends on a design square matrix, meaning that we determine the square matrix Q. I will show how it can be determined later. And there's also an expression G mu. So it depends on A mu, the unknown disturbance, and the desired velocity vector field. As I said, sometimes it's the case that we do not know what disturbances are acting on the robot, or we might not even know the weight of the micro-robot, so we can actually set it equal to 0. And in the simulation results, I will show you that without no knowledge of d mu, still we can get very good, basically, convergence results. Okay. So as we saw, we have got this formulated quadratic program. Now, there's a catch, as opposed to the case, the problem that Mark studied back in the 80s. So in the case for Mark, he was trying to induce basically inequalities on the components of the control input, meaning that the constraint on motor 1, constraint on motor 2, and so on. Here we have got in an aggregate, in a sense, an aggregate constraint in the sense that we would like to have a constraint on the whole, basically magnitude of the vector, meaning that it's not important really for us what each basically actuation input is, as long as the magnitude of the whole vector is less than a certain value. So it's basically a quadratic optimization over a sphere or a circle. We know from the optimization literature, it's called the trust region subproblem. It's a very numerically rich problem, specifically if one wants to implement it numerically and in real time on certain microcontrollers. It would, require usually a huge amount of time. Specifically, I can mention the work of Grizzle and Ames on bipedal robots. When they do online optimization, sometimes these optimizers do not converge, and they have to switch to PIDs. But if we want to do such a thing, specifically in the case of micro-robot, it would be a self-defeating solution, because if you remember from my earlier slides, one of the main goals of us was that we needed smooth velocity profile, or smooth command inputs. So in this specific case, we are very lucky, because there exists an analytical solution to this quadratic optimization problem. So specifically, if I assume I choose this design parameter, the matrix Q, in this optimization, quadratic optimization, and Q is something that we can determine by ourselves to be a diagonal matrix, then we can show that the pointwise optimal angular velocity control input is given by this closed form expression. Now, the beauty of this is that, first of all, as you can see from the expression, we do not go above the step-out frequency, which is inherent in what we want in the basically the solution of the optimization. The second thing is that it's closed form, meaning that we do not have to run online an optimization. So it's closed form, and it can be easily implemented on very even simple microcontrollers. So to recap, the main ideas of our solution is that, first of all, we use the concept of the integral line of sight vector from the marine craft control to generate a guidance law for orienting a robot towards its desired path, which is given by a line. And then we designed a control input basically that would make the velocity of the micro robot to converge to this VD, and at the same time meet the step out frequency constraint. Okay, so let's see some simulation results with each other. In these simulation results, basically, I exactly took the parameters that Jake actually used in his advanced robotics paper back in 2010. The exact environment, I think it was a corn syrup. And basically, I'm just trying to make my micro robot to converge to the line, which is the horizontal line going through PZ equal to 0. Okay, so this picture, the very first one on the left, it's basically using a non-integral LOS-based control, meaning that I do not use the dynamic variable S. I just try to play with the control gains. So if I pump up the control gain alpha D to be very large, 3 times larger than the original one, I would have a relatively good convergence, but it would come as with some price. So the price is that we will see in the, first of all, once we converge to the path, the velocity of the microswimmer would be very large. And then in the next slide, I will also show you the control magnitudes. Now, the middle one is when we use a lower gain, but we do not basically, again, the conventional one. So as you can see, we have a very poor convergence. And the last one is with a lower gain, but with the integral line, the dynamic variable S. As you can see, we have the convergence. And the very interesting thing about this control implementation is that in none of them we are setting E11 to be equal to 0, to be equal to 1, meaning that we do not assume any knowledge about the parameters of the micro robot and its fluidic environment. And second, though it has the microswimmer has got weight, in the control implementation, we are setting it equal to 0, meaning that we are assuming that we have no knowledge whatsoever of the weight. So it's the control that is taking care of, in a sense, indirectly calculating the effect of the weight and then minimizing its effect on convergence to the path. Okay, and this slide basically shows the magnitude on the control input. As you can see, for the first case, for a larger amount of time, we are at the saturation region of 2.8 hertz. And then once we start gradually to converge to the path, we see that it's a very larger value in comparison with the magnitude of the control in the case of the lower gain or the integral line of sight. Now, if you see look at the integral line of sight, you will see that once we have the convergence to the path, I mean, the control input would become much smaller. And then with this slide, I would like to thank you all. Now, I would also like to mention the coincidence, the relation to the University of Pisa. Actually, my academic genealogy, my very, I would say the very, very first academic grandparents were from the University of Pisa, specifically Pietro Paoli and Vincenzo Brunacci. So Pietro Paoli was a professor at the University of Pisa back in the 1700s, and his student was Vincenzo Brunacci. Of course, he didn't remain at the University of Pisa. He moved to, I think, the University of, if I'm not mistaken, Parma. But then his line, basically the line of children, academic children, actually extended to down throughout the ages, and I'm one of those children. So from that perspective, I'm also very thankful to the University of Pisa. And with this, please, I'm open to your questions. Thank you very much.
So thank you very much to Dr. Mohammadi and Dr. Spong for this interesting presentation. Okay, there is already one question from Jake.
Okay.
Hi, Jake.
Hey.
Nice to meet you, first of all.
Yeah, nice to meet you too. Thanks for all the mentions, all the shout outs. That's nice.
I mean, if you basically, if we didn't have your model, we couldn't do anything.
So when we developed that video that you showed, the very first video on YouTube of the 3 micro swimmers, that was a video we made in Brad's lab at ETH. One problem that you see with these, if you're swimming these swimmers in a horizontal plane and you're looking from the top down in a microscope like that, is they typically sink to the bottom or they rise to the top, one of the two, but sinking to the bottom is more common. And then you're rotating them to propel them forward, but then they actually roll on the surface. Even if they're not touching the surface, they roll like a wheel in addition, right? So as they swim forward, they also kind of drift to the right or left. And when we developed that gravity compensation paper that you used, we thought that there should be some way to basically apply the same techniques to solve that rolling problem as well. But we did never look into it. And I suspect your method would solve that rolling problem well. And I'm wondering if you already have tried to model that in some way.
No, not yet, not yet. But I would be definitely happy to basically see how much we can push this control methodology forward. So I think that, and correct me if I'm wrong, but if H1 and H2, the hypothesis H1 and H2 are satisfied, and let's say we are in an ideal world and we satisfy these 2 hypotheses. So let me show you that actually you also use in your advanced robotics paper. Do we still run into the problem of rolling? Meaning that if we have got the perfect synchrony with the external field and also the central axis.
Yeah, because basically if you're using a uniform field, you can find that your microrobot can be pointing in the right direction. It's still pointing forward. It's just drifting to the side as it's moving forward, right? Okay. So your orientation is correct. Your forward velocity is what you wanted, but you just have this, it's like a disturbance. Because, you know, you're spinning this way and your viscosity below you, between you and the surface is higher effectively than above you. And so you roll, even if you don't touch.
So I think that then this might be this dynamic compensation embodied in this integral action might be able to capture those disturbances. If, let's say, the roll is being induced by some fluidic unknown forces, but we definitely need to look into it. No, you're absolutely right. And let me also give you an interpretation of why this action is very good. So let's assume for a moment that actually my micro robot is exactly on the line, and it's moving on the line, and then there comes a force which would perturb, basically deviate the micro robot from the line a little bit. What would happen is that then, as you can see, this distance from the line would become larger than 0. It would be non-zero anymore. Then that's the moment when this integral action kicks in. And it acts in a way that would make, the robot to reconverge to the path. So if you think of the PID controller in a way, its action is like the integral action, the PID. It would reject the action of the disturbances. But I'm definitely pretty much interested actually to continue this talk with you, hopefully maybe having some meeting next week or 2 weeks from now and discuss it more.
Yeah, sure.
But definitely your line of research has been, basically the foundation of this work.
I'd be happy to do that.
Thank you very much. Really appreciate it.
So there is time for another quick question.
Sure.
Very, very quick. First of all, thank you for the interesting talk. It was very good. I didn't meet the colleagues from Pisa. I'm not old enough, but it's nice to have the citation. One very quick point. So when you have this rolling effect that Jake described, you also miss the target, right? So your target is to progress in this line, but if you switch, I mean, if you move on a parallel line, then of course the orientation is the same, but with respect to the target, you're making an angular error, right? So I guess what Alireza said is that you might have this heading error in the control law.
Mm-hmm.
Correct?
True. Very true. And actually, let me show you this, and let me, if I can zoom in also as well on the picture, specifically, if you look at the so do you see in the integral action? So it's like just like a human Kubernetes or the sailors that once they want to converge to that line, they dynamically steer the ship. It's exactly like that, and I think that it's related exactly to what you mentioned. So if you look at even in the case for the non-integral based, it's always heading towards basically one direction and only one direction, because there is no dynamic compensation. Now, if you have a very strong control authority, then of course you can converge, but from a control effort perspective, the price to be paid is very high. And again, as you can see here, again, in a sense, a constant. But here we have got this dynamic movement of looking ahead, just exactly like the ships and how the sailors would orient their boats when they're moving on a flow.
But what do the black arrows represent?
So it's the velocity of the micro robot. Okay. So the
tangent,
VD,
the tangent of the curve, yeah.
Yeah,
but
the VD, yes.
But one thing that maybe isn't clear to like Antonio and other people who don't work in this is throughout your project, you're not penalizing orientation error at all, basically, right? You're treating the micro robot like it's a point, which is essentially its center of mass, and you're just trying to control its position in space, and you're letting the orientation be whatever it needs to be to accomplish that, right?
Yes, absolutely true.
And that's true. He's doing that whether he's considering this rolling effect or not. That's built into the assumption.
Yes, true.
But there is a notion of heading, right?
Yes, there's a notion of heading in terms of basically the velocity of that center of mass, that point mass, where it's heading at, where it's looking at. So specifically given by these vectors, velocity vectors.
Because your input is changing the attraction force, but also the heading of in your assumption, you have that the axis of the swimmer is aligned with the field, right?
Yes, exactly.
So if you change the alignment of the field, then you can correct the heading. Am I wrong?
No,
I'm just an outsider. I'm likening it to the ship that you showed there.
Yes. So first of all, our only measurements are the position of the micro robot in the plane. So PX and PZ, no orientation. Now we don't sense any orientation, but as long as we can basically ensure that H1 and H2 are satisfied, those two hypotheses, then alignment is embodied in. So alignment of the axis of the micro robot and the basically magnetic field are embodies in those hypotheses. Now, one of the things that the control design is taking care of is that automatically it would satisfy those hypotheses. So, for instance, if there's a jump in the, so suppose that the human is just commanding the velocity of the microrobot. If the human inserts a jump velocity, a jump in the velocity command, then the alignment would go away. Now, a smoothness and continuity is one thing that we would ensure in this control design. So from that perspective, because we have this smoothness in the commanded inputs, the alignment is always guaranteed.
Okay, thank you very much. Very interesting. I need to make myself more familiar with the model.
No, sure. Actually, I would be happy to send you the paper.
Yes, please do.
No, sure.
Okay, so we have arrived at the end of the first day of robotics gym sessions. So my apologies if we went long with the presentation, but it has been a very exciting day of excellent research presented by excellent researchers. So thank to all the speakers and the attendees of the event. And we will see tomorrow for another day of exciting presentations and PhD thesis discussions. Thank you very much.
Thanks, everybody.
Thank you very much.
Thanks
Thank you,
for the
everybody.
Thank you.
Thank you. Bye-bye.
Bye-bye. Have a good night.
Bye.
Good night. Ciao, Paul.
Ciao.
Thank you, Mark, for coming.